Something stirs in the dark, a ghost, burning slow through the endless night. Its name is Mira, a red giant, a dying sun, a relic of cosmic fire drifting through the sea of stars. It moves like a wounded ember, leaving behind a glowing scar 13 light-years long, a luminous wound across the fabric of the galaxy. For centuries, humanity believed stars perished in silence, their final breaths dissolving gently into space. Mira shattered that illusion. When NASA's ultraviolet eyes turned toward it, they did not see stillness. They saw motion, a stream of light, a ribbon of energy, a stellar scream twisting through the void. It was as though the universe itself had been guarding a secret too vast, too ancient, too luminous to hide any longer. Mira lives about 300 light-years away in the watery domain of Cetus, the constellation of the Whale. From that distant corner of the sky, it performs a slow, rhythmic dance of death and rebirth. It grows bright, fades away, and then returns again, completing this cycle roughly every 11 months. Sometimes it flares so vividly that anyone on Earth can see it with their naked eyes. Other times, it vanishes into invisibility, leaving astronomers straining through telescopes to find even a hint of its glow. That strange heartbeat, the steady rise and fall of Mira's light, became one of the great turning points in astronomy. When it was first noticed in the late 1500s by the Dutch astronomer David Fabricius, no one could quite believe what they were seeing. Fabricius thought he had found a nova, a star suddenly erupting into brilliance. But the light returned. It dimmed, brightened, dimmed again. Stars, it seemed, could change. And with that revelation, the myth of an eternal, unchanging sky began to die. The name Mira, Latin for wonderful or astonishing, was given later in the 17th century by Johannes Hevelius, who understood how fitting it was. Because Mira is not just a star, it is an archetype, the first known of its kind, the original variable star. Today, astronomers call all stars of this pulsating type Mira variables, honoring the one that started it all. Inside Mira, deep beneath the crimson haze of its outer layers, fusion falters. Hydrogen and helium burn in unstable shells, creating waves of expansion and contraction. As the star swells, its surface cools. As it shrinks, the heat returns. The result is a rhythmic flicker, the pulse of a dying heart that has outlived its calm and entered the storm of its own decay. Over each pulsation, Mira sheds a little more of itself into the cosmos. Its outer layers, no longer held tightly by gravity, drift away as glowing dust and gas, the ingredients from which new stars and planets will one day form. Every shimmer of Mira's light is a whisper of renewal, a promise that nothing in the universe truly ends, it only transforms. But the most haunting feature of all is the trail. 13 light-years long, that's nearly 80 trillion miles, a colossal plume of matter streams behind Mira as it races through interstellar space. In 2007, NASA's Galaxy Evolution Explorer, GALEX, captured it, an ethereal ribbon glowing in ultraviolet, stretching farther than any stellar tail ever observed. Like a cosmic comet, Mira leaves a permanent trace of its passage, a kind of starlight graffiti written across the galaxy. Imagine it. If you could travel alongside this red giant, you would see a vast wake of shining debris, curling behind it like smoke from an ancient torch. That trail tells a story written not in words, but in atoms, carbon, oxygen, and nitrogen, the very elements that make up our bodies, our air, our oceans. Mira, in dying, is seeding life into the darkness, and yet, even as it unravels, it still binds itself to a companion. Mira is not alone. It is part of a binary system, Mira A, the red giant, and Mira B, a smaller, hotter partner orbiting nearby. Together, they enact a slow gravitational waltz, exchanging material and energy in a delicate, violent balance. Mira B feeds on the outflow of Mira A, drawing in its expelled gases, forming an accretion disk of heated matter. To watch them is to witness the raw intimacy of stellar death, one star fading, another feeding, the pair forever intertwined. If Mira were placed in the heart of our solar system, its swollen body would swallow Mercury, Venus, Earth, and reach past the orbit of Mars. It is nearly 400 times the size of our sun, but its density is astonishingly low, more like fog than fire. Its atmosphere so diffuse that a spaceship could plunge deep into its outer layers without immediate destruction. Look up at Cetus, that ancient whale from Greek myth, and somewhere in its southern flank, Mira pulses, the wonderful star, the first variable, the cosmic beacon that refuses to fade quietly. Its light that reaches us tonight left the star more than 4 centuries ago, when Galileo was just turning his telescope to the heavens for the first time. The photons that strike our eyes are older than modern science itself. Mira is a dying star, yes, but it is also a teacher. Through its rhythm, we learned that the universe is not static. It breathes, it changes, it evolves. Mira's cycle of brightness and darkness became the heartbeat of stellar evolution, guiding astronomers to understand how stars live, die, and are reborn in the dust they leave behind. Even now, Mira continues to astonish. Every pulse, every flare, every faint shimmer of ultraviolet light is another echo in the long symphony of the cosmos. It is both an ending and a beginning. A wonder still burning in the dark, a ghost that refuses to vanish, and somewhere out there, 13 light years behind it, its trail still glows. A testament to everything a dying star can give before it finally fades to silence. However, during its dimmest phases, it fades so profoundly that even seasoned stargazers must rely on telescopes to glimpse it. The transformation is so dramatic that it appears as if the star vanishes into the black velvet of space, only to re-emerge months later, radiant and defiant against the dark. For centuries, this cosmic heartbeat, this rhythmic breathing of light, has fascinated astronomers and dreamers alike. The star's name, Mira, meaning wonderful or astonishing in Latin, could not be more fitting. It embodies the awe and reverence early observers felt when they saw her that refused to remain constant, a celestial body that seemed almost alive. Its discovery as a variable star in 1596 by the German astronomer David Fabricius marked a turning point in astronomy. Until that time, the heavens were thought to be unchanging, eternal, and perfect. Mira shattered that illusion. Here was a star that defied the notion of cosmic permanence. Alongside the brief brilliance of novae and supernovae, Mira stood as one of the first known stars to show that even the heavens evolve and fade. Mira is a red giant, a dying star in the final chapters of its stellar life. As its internal fusion slows, it swells to a vast size, its outer layers drifting outward and cooling. Every few hundred days, it pulses like a living organism, expanding and contracting as if gasping for breath. When it expands, its surface cools and the light dims. When it contracts, it heats up and its brilliance returns. Each pulse sends waves of material flowing outward into space, forming a thin, ghostly shell of gas and dust that glows faintly around it. Through powerful telescopes, this halo can be seen spreading across light years, a fragile shroud marking the star's gradual unraveling. At its brightest, Mira can reach a magnitude near 2, bright enough to be seen without a telescope. For a time, it shines among the familiar patterns of the winter constellations, rivaling stars in the Big Dipper in its visibility, yet within months it begins to fade. By the time it reaches its faintest phase, around magnitude 10, it becomes invisible to the naked eye. Only patient observers with telescopes can find it then, a dim ember hidden in the constellation Cetus, the sea monster. This cycle of light and darkness repeats roughly every 11 months, giving Mira its place as the prototype for a whole class of similar stars now known as Mira variables. These stars share a remarkable characteristic: long, rhythmic changes in brightness lasting from 80 days to 1,000. They represent red giants in their twilight, unstable and magnificent, their outer layers heaving like ocean tides driven by forces deep within. Each pulsation tells a story of energy struggling to escape, of a star balancing on the edge between life and death. The study of Mira and its kin has revealed much about the fate of stars like our Sun. One day, billions of years from now, the Sun too will swell into a red giant, its surface expanding past the orbits of Mercury and Venus. It will pulsate, shedding its outer layers, perhaps forming a cloud of glowing gas not unlike the one surrounding Mira. In that distant future, another species, if any exists, might gaze upon our dying star and see it flicker in the night sky, just as we now watch Mira fade and return. Variable stars like Mira are more than celestial curiosities. They are cosmic storytellers. Each change in brightness is a message encoded in light, revealing secrets of a star's mass, temperature, and inner structure. Unlike most stars that appear steady to the human eye, variable stars remind us that change is a universal constant. Some pulsate rhythmically, their light rising and falling with clock-like precision. Others vary unpredictably, their brightness fluctuating as magnetic storms or eruptions disturb their surfaces. Among the pulsating types, Cepheid variables hold a special place. Their periods of brightness variation are directly related to their intrinsic luminosity. By measuring how long a Cepheid takes to complete one cycle, astronomers can determine how bright it truly is, and from that, calculate its distance from Earth. This discovery, made in the early 20th century, became one of the most powerful tools in cosmic measurement. Through Cepheids, astronomers could map the Milky Way, measure the size of the universe, and even discover that galaxies beyond our own exist. Other variable stars tell different stories. Our Lyrae stars, for instance, are ancient, low-mass pulsators found in the dense globular clusters that orbit our galaxy. Their rhythmic flicker offers insight into the early history of the Milky Way. Eruptive variables, on the other hand, are more violent by nature, stars that flare up unpredictably due to magnetic disturbances or cataclysmic events on their surfaces. Still more extreme are novae and supernovae, whose sudden explosions can outshine entire galaxies for a brief moment before fading away. There are also eclipsing binaries, pairs of stars locked in close orbits around one another. As one passes in front of the other, their combined brightness dips from our point of view. These systems act as cosmic laboratories, allowing astronomers to measure stellar masses and orbital dynamics with remarkable accuracy. The famous star Algol, known since antiquity as the demon star, is one such system. Its regular dimming, once thought to be a sign of supernatural influence. Every type of variable star, from the gentle pulsators to the explosive novae, contributes a piece to the grand puzzle of stellar evolution. Together, they reveal the intricate balance of gravity, pressure, and nuclear fusion that governs a star's existence. By observing their rhythms, astronomers learn not only how stars live and die, but also how the elements that form planets and life itself are forged and dispersed into the cosmos. In the quiet hours of night, when telescopes turn toward Cetus and Mira rises once more to its brightest phase, one cannot help but feel a sense of connection. The light that reaches us today left the star centuries ago, traveling across interstellar space to tell a story older than civilization itself. A story of transformation, of endings and beginnings. Mira's light is not merely illumination, it is memory. It is the shimmering echo of a dying star's final performance, a slow, graceful waltz of brightness and shadow across the dark stage of the universe. And as we watch it fade and return, we are reminded that even in the vastness of space, nothing truly remains still. Everything breathes, everything changes. Furthermore, the study of variable stars has not only expanded our understanding of stellar behavior, but has also reshaped our comprehension of the universe itself. These stars, whose brightness changes over time, act as cosmic beacons, silent messengers carrying information about distances, ages, and the very fabric of space. It was through the study of such stars, particularly Type Ia supernovae, that astronomers uncovered one of the most astonishing truths in modern cosmology. The expansion of the universe is accelerating. This revelation overturned long-held assumptions about cosmic evolution and earned the scientists behind it the Nobel Prize in Physics. The flicker of a single distant star had, in essence, rewritten our cosmic story. As researchers continue to observe and decode the rhythmic pulses and subtle fluctuations of variable stars, they peel back layer after layer of the universe's mystery. These celestial oscillations are far more than random twinkles in the night sky. They are encoded signals, revealing the internal mechanics, life cycles, and destinies of stars. Every change in brightness tells a story of pressure, temperature, and fusion deep within a star's heart. Among the most important of these stellar storytellers are the Cepheid variables. These pulsating stars maintain a precise relationship between their luminosity and their pulsation period. The longer the period, the brighter the star. This simple yet profound correlation has allowed astronomers to use Cepheids as standard candles to measure cosmic distances across unimaginable scales. By tracking these pulsations, scientists can map the architecture of galaxies and even estimate the size of the observable universe. The legacy of Henrietta Swan Leavitt, who first uncovered this relationship in the early 20th century, continues to guide astronomers through the darkness of space more than a century later. Another key group, the RR Lyrae variables, consists of older, low-mass stars often found in ancient globular clusters. These stars are the quiet elders of our galaxy, offering vital clues about the Milky Way's early formation. By studying their rhythmic light patterns, astronomers can probe the internal structures of these aged stars and reconstruct a timeline of galactic evolution, tracing how the cosmos transitioned from its turbulent youth to its present state of complexity. Yet, the story of variable stars also illuminates the final chapters of stellar life. Mira variables, red giants nearing their end, are particularly fascinating. Mira itself, also known as Omicron Ceti, is the archetype of this class. It swells and contracts in grand cycles lasting from 100 to 1,000 days, its brightness changing by a factor of roughly 1,000. At its peak, Mira glows brightly enough to be seen without a telescope. At its dimmest, it fades nearly into invisibility. Each pulsation represents the slow unraveling of a dying star, as it sheds its outer layers into space. These expelled elements, carbon, oxygen, nitrogen, seed the cosmos with the raw materials for new stars and planets, including the building blocks of life. Through this process, the death of one generation of stars paves the way for the birth of the next. The study of variable stars relies on an array of advanced instruments that capture and interpret their faint whispers of light. Ground-based telescopes form the backbone of these observations, using sensitive charge-coupled devices, CCDs, to detect even the slightest variations in brightness. Spectroscopes add another layer of insight, breaking starlight into its component wavelengths to reveal temperature, composition, and motion. Each spectral shift or flicker becomes a clue, evidence of pulsations, stellar winds, or the gravitational tug of a companion star. Above Earth's turbulent atmosphere, space-based observatories like the Hubble Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, observe with unmatched precision. Free from the distortion of air and weather, they can measure minuscule fluctuations in light that ground-based observatories might miss. Photometers aboard these satellites record exact measurements of brightness over time, creating light curves, visual fingerprints of a star's changing luminosity. From these data, astronomers can determine a star's type, pulsation period, and even its distance from Earth with astonishing accuracy. The journey of discovery began centuries ago. In the 16th century, early astronomers noticed that certain stars appeared to flicker or change in brightness, defying the ancient belief that the heavens were static and eternal. Over time, as observational tools improved, these mysterious stars were cataloged and classified. Some pulsed in predictable cycles, others dimmed because a companion star eclipsed them. The expanding classification of variable stars marked a pivotal step toward understanding the dynamic, ever-changing nature of the cosmos. Even today, not all discoveries come from massive observatories or complex instruments. Amateur astronomers, armed with dedication, modest telescopes, and a passion for the stars, play an essential role in this field. They monitor long-term variations that professional observatories cannot continuously track, providing data spanning years or even decades. Many amateurs have discovered new variable stars, expanding our celestial catalogs and sometimes identifying rare or transient phenomena. When an unexpected outburst or dimming occurs, these observers are often the first to notice, alerting professional astronomers who can then direct powerful telescopes to capture the fleeting event in detail. In this way, the partnership between amateurs and professionals weaves together countless points of light into a coherent narrative of stellar evolution. Through all these efforts, the study of variable stars connects the intimate with the infinite, the flicker of a single point of light with the expansion of the entire cosmos. Each changing star reminds us that the universe is not a static backdrop, but a living, breathing expanse, filled with cycles of birth, transformation, and decay. In every pulse and shimmer, we glimpse both the fragility of existence and the enduring rhythm of the stars, a rhythm that has been echoing across the cosmos for billions of years, waiting for us to listen. However, at its faintest, the star fades until even the sharpest human eyes cannot detect it without the aid of a telescope. This transformation, both subtle and dramatic, unfolds over roughly 330 days, a slow, cosmic heartbeat that has fascinated observers for centuries. The light of this celestial body does not simply dim and brighten by chance. Instead, it follows a rhythmic pattern driven by the deep and intricate workings within the star itself. As the star expands, its outer layers cool and its light reddens, its surface swelling to dimensions far beyond its resting state. Then, as if inhaling after a long exhale, it contracts once more, the surface heating and the glow intensifying. This delicate dance of expansion and contraction is governed by changes in the opacity of the stellar material, particularly in the layers of ionized helium that alternately trap and release energy. The result is a mesmerizing cycle of pulsations that, when seen from Earth, creates the illusion of a star that breathes with light. Astronomers have long been captivated by this particular star, known as Mira, the Wonderful. Located in the constellation Cetus, Mira serves as the prototype for an entire class of stars now called Mira variables. Its discovery and subsequent study revolutionized humanity's understanding of the heavens. When it shines at its brightest, Mira can be seen without any optical aid, a solitary point of flickering light that seems almost alive. Yet, within months, that same star retreats into obscurity, its brilliance sinking below the threshold of naked eye visibility. This extraordinary transformation, its brightness shifting by a factor of about 1,000, marked Mira as something unique when it was first recorded by early astronomers more than 4 centuries ago. They marveled at how a star could appear and vanish within the span of a single year. Today, with modern instruments and centuries of accumulated data, we understand that Mira is not alone. It is the namesake of a vast family of long-period variable stars scattered across the Milky Way and beyond. Mira variables are, in essence, dying stars, red giants nearing the end of their lives. Having exhausted the hydrogen in their cores, they now fuse helium and heavier elements, their internal balance teetering between collapse and expansion. Their outer envelopes balloon to immense proportions, their surfaces cool to a deep crimson hue, and their diameters can swell to several hundred times that of the Sun. In this unstable state, their outer layers pulse like the steady beat of a drum, causing the periodic rise and fall in brightness that we observe. For astronomers, Mira's predictability, its steady rhythm and dramatic range of brightness, made it an ideal candidate for careful study. Over time, it became the standard against which all other long-period variables were measured. Observations of Mira and its kind have revealed that their pulsations are not merely surface phenomena, but clues to profound internal processes. These stars act as living laboratories, teaching scientists how matter behaves under extreme temperatures and pressures, and how stars evolve as they approach their final stages. The pulsations do more than modulate light. They actively reshape the stars themselves. Each expansion and contraction carries energy outward, helping to lift vast quantities of gas and dust into surrounding space. Mira variables are therefore among the universe's great contributors to the interstellar medium. The material they shed, rich in carbon, oxygen, and other heavy elements, will someday condense into new stars, new planets, and perhaps even the building blocks of life. In this way, the death throes of a single red giant become the seeds of future cosmic creation. Thousands of these stars have now been identified throughout our galaxy, about 6,000 officially classified as Mira variables, though that number continues to grow as technology advances. Modern sky surveys, armed with automated telescopes and sensitive detectors, uncover new members of this family almost daily. Their rhythmic flickering can be seen not only in our Milky Way, but also in neighboring galaxies, such as the Magellanic Clouds and Andromeda, proving that the life cycles of stars follow universal patterns across the cosmos. Mira's story is therefore not only the story of one star, but of an entire phase in the grand life of stars. Each Mira variable embodies the slow, luminous end of stellar existence, a final brilliant performance before fading into the silence of a white dwarf. To watch these stars is to witness the aging of suns, to glimpse the forces that recycle the elements of the universe, and to understand that even in their decline, stars remain creators. Through their light fading and returning in a steady cosmic rhythm, Mira and its kin remind us of the continuity of creation and destruction that defines the universe. Their brilliance is not a final gasp, but a gesture of generosity, a final act of giving as they scatter the ingredients for future worlds into the dark, waiting sky. And yet, the story of the Mira variables is not just one of pulsation and fading light. It is the story of the universe breathing. These stars, immense and trembling with energy, act as cosmic metronomes whose rhythmic expansions and contractions have guided astronomers in mapping the vastness of space. Their predictable relationship between how fast they pulsate and how bright they shine has become one of the most powerful tools in measuring distance across the galaxy. Each pulse is a message, traveling through the cosmic dark, telling us not just where they are, but how far the edges of our understanding can reach. Through their steady beat, scientists refine the scale of the cosmos, tracing the invisible scaffolding that binds galaxies together. But Mira variables do more than help us measure, they build. As they age, these red giant stars become crucibles of creation, their interiors forging new elements that will one day become the ingredients for planets, oceans, and even life itself. When they swell and contract over hundreds of days, their outer layers become unstable, and the stars begin to lose mass through powerful stellar winds. These winds carry away vast clouds of carbon, nitrogen, and oxygen, elements created in the furnace of the star's heart through nuclear fusion. Every breath the star exhales enriches the space around it. Within those shimmering clouds, new stories begin. Inside these dying titans, even heavier elements are being born through a slow but extraordinary process known as neutron capture, or the S process. Here, within the dense, seething depths of a star nearing its end, neutrons are gradually absorbed by existing atoms, building new ones heavier than iron, elements like barium, strontium, and lead. When the star finally releases its outer layers, these new atoms are cast into interstellar space, joining the vast tapestry of cosmic dust that fills the void between stars. This material, once part of a living, pulsating giant, drifts silently until gravity gathers it again into new stars, new planets, perhaps even into the cells of living beings billions of years later. Over the course of countless generations, this cosmic recycling transforms the universe itself. What begins as simple hydrogen and helium from the early cosmos evolves, through the lives and deaths of stars like the Mira variables, into a universe rich with complexity. Each Mira variable, though just one among billions, contributes to this chemical evolution, shaping galaxies, seeding future worlds, and ensuring that the story of creation continues in endless cycles of birth, death, and rebirth. The Mira variable stars, named after their prototype, the star Mira in the constellation Cetus, represent one of the most fascinating chapters in stellar evolution. These red giants are nearing the end of their long, luminous lives. After billions of years of burning hydrogen in their cores, they have exhausted their primary fuel and expanded to staggering sizes, often hundreds of times the diameter of our sun. Their outer layers swell and cool, giving them a deep crimson hue, while their interiors churn with complex nuclear reactions and unstable pressures. Their brightness can change dramatically over time, sometimes by a factor of several magnitudes, over cycles that last anywhere from 100 to 1,000 days. It is a slow, majestic heartbeat written across the night sky. A Mira variable remains in this pulsating state for perhaps a few 100,000 years to about 1 million years. Brief in cosmic terms, yet rich in transformation. As the star pulsates, it sheds its outer layers in waves of gas and dust, forming vast glowing shells that expand into the surrounding darkness. These clouds, illuminated by the dying light of the star, are what astronomers call planetary nebula. The term, though misleading, dates back to early astronomers who, peering through their small telescopes, saw these ghostly orbs and mistook them for planets. In truth, they are the final, delicate exhalations of a dying sun. Eventually, the Mira variable reaches its quiet end. The last of its outer material drifts away, leaving behind a small, dense core, a white dwarf. This remnant, roughly the size of Earth but containing nearly the mass of our sun, glows faintly, slowly cooling over billions of years. It will never shine as it once did, but its light carries the memory of the star that was. In time, even that faint glow will fade, leaving behind a dark, silent relic. And yet, this is not a story of endings. It is a story of transformation, of how the death of one star gives rise to countless others. The carbon in your body, the oxygen in your lungs, the iron in your blood, all were once part of stars like these. The Mira variables, in their grand and rhythmic decline, have written their legacy across the cosmos. Every twinkling point of light in the night sky, every world that has ever formed, owes part of its existence to the pulsations of these ancient red giants. Through them, the universe remembers and continues to create. However, for the most massive of the Mira variables, those that begin life with several times the mass of our Sun, the story of their demise takes a far more dramatic turn. These colossal stars do not fade quietly into the night. Instead, they die in cataclysmic outbursts so luminous that for a brief moment they can outshine entire galaxies. This is the supernova, one of nature's most spectacular finales. The precise point at which a star tips into this explosive fate remains one of the enduring mysteries of stellar astrophysics, a boundary that astronomers continue to probe through observation and theory. When a Mira variable reaches the twilight of its life, the transformations it undergoes are nothing short of cosmic theater. These pulsating red giants, known for their rhythmic brightening and dimming, begin to falter as the nuclear reactions that sustain them for millions of years exhaust their final reserves of fuel. With nothing left to counter the crushing pull of gravity, the star's delicate balance collapses. It begins to shed its outer layers in vast, billowing waves, layers that drift outward into the surrounding interstellar medium, carrying with them the chemical treasures forged in the heart of the dying star. The result is a breathtaking spectacle, a planetary nebula. This glowing cloud of gas and dust, often spanning several light years, is illuminated by the exposed core of the dying star. That core, now stripped of its outer shell, becomes a white dwarf, a dense, Earth-sized ember containing roughly the same mass as the Sun. From its blistering surface, ultraviolet radiation floods the nebula, causing it to shimmer with soft hues of blue, red, and green. Over time, this ethereal veil of gas disperses, its elements, carbon, nitrogen, oxygen, seeding the galaxy with the building blocks of future stars, planets, and perhaps even life itself. The death of a Mira variable, then, is not merely an end, it is a renewal. Through destruction, it bequeaths the raw material for creation, feeding a cosmic cycle that has persisted since the dawn of time. Each atom of carbon in our bodies, every molecule of oxygen we breathe, was once forged in the furnace of a dying star. In that sense, the life and death of a Mira variable reach far beyond its own corner of the cosmos. They echo in the story of everything that exists. Mira, or Omicron Ceti as it is formally known, is one of the most studied and beloved examples of these enigmatic variable stars. Situated about 350 light-years from Earth in the constellation Cetus, Mira is not a solitary beacon but a binary system. Its main component, Mira A, is the red giant that lends the system its fame, while its faint companion, Mira B, orbits close by, locked in a gravitational dance that has persisted for millennia. Astronomers estimate that Mira A possesses about 1.2 times the mass of our Sun, a seemingly modest figure, yet one that hides extraordinary complexity. What makes Mira so compelling is not merely its mass, but its behavior. Its brightness waxes and wanes with remarkable regularity, sometimes bright enough to be seen without a telescope, then fading until it nearly disappears from view. These pulsations, driven by rhythmic expansions and contractions of the star's outer layers, make Mira a cornerstone in our understanding of stellar evolution. Each pulse is a heartbeat of a dying giant, a signal from a star slowly unmaking itself. In its current phase as a red giant, Mira has swelled to a staggering size. Its radius has expanded hundreds of times beyond that of our Sun. If Mira were placed where our Sun sits at the center of the solar system, its swollen surface would extend far beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and the red planet alike. To imagine the scale, consider this. If our Sun were reduced to the size of a golf ball, Mira would be as large as a two-story house. And yet, despite this vast expansion, Mira is surprisingly delicate. Much of its volume is composed of thin, diffuse gas, giving it an average density far lower than that of our Sun. This immense size comes at a cost. Mira's outer layers are only weakly bound by gravity and are slowly escaping into space, forming a stellar wind that drifts outward like smoke from a fading fire. This slow shedding of mass is part of the reason the star's life is nearing its end. It is literally evaporating into the cosmos. Over time, these escaping gases will form a nebula that glows for tens of thousands of years before fading into the galactic background, leaving only the white dwarf at its center as a silent remnant of what once was. The surface of Mira is also far cooler than that of our Sun. At its dimmest phase, its temperature drops to about 2,700 degrees Celsius, roughly half that of our Sun's steady 5,500 degrees. This cooler temperature gives Mira its deep crimson hue, a visual hallmark of aging stars nearing the end of their lives. Yet even in this decline there is beauty. The star's light flickers gently through our telescopes, a living reminder that the universe is both fragile and eternal. To watch Mira is to witness time itself, the rise and fall of stellar life, the relentless cycle of birth, death, and rebirth that shapes our galaxy. Every shimmer of its fading light carries a message from across the gulf of space. Even in dying, a star can give birth to worlds yet unborn. However, the star known as Mira does not remain cool for long. As it swells and contracts in a ceaseless rhythmic pulse, its surface temperature rises to a staggering 3,500 degrees Celsius, hotter than molten metal, hot enough to reshape the chemistry of its own atmosphere. This cycle unfolds over the course of roughly 11 months, during which Mira's brilliance waxes and wanes dramatically. At its peak, the star can blaze up to 1,000 times brighter than when it lies in its faintest phase, transforming from a barely perceptible red ember into one of the most luminous beacons in the night sky. These extraordinary changes in brightness are more than just a visual spectacle. They are the outward signs of deep, powerful processes unfolding within the star's core. As Mira expands, its outer layers stretch outward, cooling and dimming. Then, under the crushing weight of its own gravity, the star contracts again, its surface heating up and glowing more fiercely. This pulsation, a cosmic heartbeat, is driven by the complex dance of forces inside the star's interior, where helium fuses in a thin shell surrounding a dense carbon-oxygen core. In this inner crucible, temperatures soar to millions of degrees, and the energy released by fusion pushes outward, fighting against gravity in a delicate equilibrium that defines Mira's existence. At the star's coolest, when it swells to its greatest size, the surface temperature drops to about 2,700 Kelvin, cool enough that molecules begin to form in its outer layers, creating a ruddy, dusky glow. At this stage, Mira fades from view, nearly invisible to the naked eye. But as the cycle continues and the star contracts, its surface heats up again, reaching roughly 3,500 Kelvin. The result is an 800-degree swing that fuels its transformation from faint to blazing bright. Each cycle of expansion and contraction takes about 330 days, nearly a full Earth year, marking time in the slow, steady rhythm of stellar life. These fluctuations offer astronomers a remarkable window into the late stages of stellar evolution. Mira, also known as Omicron Ceti, represents a phase our own sun will one day reach billions of years from now. It is a red giant, a star nearing the end of its life, having exhausted the hydrogen that once fueled its core. In its place, helium burns in a shell around a dense, cooling remnant of carbon and oxygen. This transition marks a turning point. The star is no longer stable. Its outer layers throb and shimmer with instability, its light and heat ebbing and flowing as the delicate balance of forces within it shifts. Spectroscopic studies of Mira's light reveal a rich tapestry of elements, not just hydrogen and helium, but heavier elements forged in its own fiery interior. Among these are titanium, vanadium, zirconium, and even technetium, a radioactive element not naturally found on Earth. The presence of technetium is particularly significant. It proves that Mira is actively creating new elements through nuclear fusion and bringing them to its surface through powerful convective currents. In this way, Mira is both a laboratory of nuclear physics and a cosmic recycler, enriching the galaxy with the raw materials from which new stars, planets, and eventually life itself will form. But Mira is more than just a pulsating furnace. It is also a traveler, racing through our galaxy at incredible speed, moving at about 130 kilometers per second. That's over 460,000 kilometers per hour. It plows through the interstellar medium like a ship cutting through cosmic seas. As it travels, Mira leaves behind a vast tail of gas and dust, stretching an astonishing 13 light-years across space. a glowing ribbon visible only in ultraviolet light. This tail, shaped by the interaction between Mira's stellar wind and the thin interstellar gas it encounters, stands as silent evidence of its restless journey across the Milky Way. Over the centuries, astronomers have watched Mira with wonder. Its dramatic variability was first noted in the 17th century, making it one of the earliest known variable stars. Even today, it continues to captivate both professionals and amateurs alike, a living, breathing embodiment of stellar change. For scientists, each fluctuation in brightness is a clue, each spectral shift a whisper from the heart of a dying star. For observers, Mira's transformation is a reminder that the heavens, though seemingly eternal, are in constant motion. Stars are born, live brilliant lives, and then fade, scattering their essence back into the cosmos. Inside Mira, the story of creation and destruction plays out with unrelenting rhythm. The triple alpha process, in which 3 helium nuclei combine to form carbon, continues in the star's dense core, releasing the energy that fuels its pulse. As the helium supply dwindles, Mira's destiny approaches. Eventually, it will cast off its outer layers entirely, forming a glowing planetary nebula that will drift through space for tens of thousands of years. At its heart, the once mighty red giant will leave behind a tiny, dense white dwarf, a stellar ember no larger than Earth, but with a mass comparable to the Sun's. For now, though, Mira continues its performance, expanding, contracting, glowing, dimming, a silent metronome in the night sky. Through telescopes, we see not just a star, but a glimpse of the universe's grand design, matter born in fire dispersed into space and destined to rise again as new stars and worlds. Every shimmer of Mira's light tells part of that timeless story, a story of energy, transformation, and the ceaseless cycles that shape the cosmos itself. And so, amid the quiet vastness of the constellation Cetus, a single crimson point of light beats like a cosmic heart. Mira, also known as Omicron Ceti. For centuries, it has captivated the human imagination, not for its constancy, but for its change. To the naked eye, it appears and disappears in cycles, a star that fades into obscurity only to blaze back into brilliance months later. Its rhythmic pulsations, lasting about 11 months, make it one of the first variable stars ever discovered. Yet, beneath this celestial flicker lies the story of a dying giant, a star in the twilight of its existence. Mira's life began humbly, billions of years ago, as a star much like our sun. Back then, it burned with a steady, youthful light, converting hydrogen into helium deep within its core. It shone bluish-white, smaller and hotter than it is today, and rotated rapidly, surrounded by a disk of gas and dust from which planets might once have formed. For billions of years, this serene stability continued. Then, slowly, almost imperceptibly, change began. The hydrogen at its center was spent, and the delicate balance between gravity and radiation faltered. Mira expanded, enormously, its outer layers swelling outward until it became a vast red giant, roughly 400 times the diameter of our sun. Now, Mira's surface is a restless ocean of convective cells, each one larger than Earth itself. Its outer layers churn and heave, unstable and thin, a fragile shell enveloping a dense, exhausted core of carbon and oxygen. Deep within, hydrogen and helium still burn, but only in thin shells surrounding the inert center. These burning shells alternate in dominance, creating thermal pulses that cause the entire star to contract and expand, brightening and dimming with each cycle. This is the heartbeat astronomers see from Earth, a slow, majestic rhythm marking the final stages of stellar life. But Mira's instability runs deeper than its flickering light. Its magnetic field, a force invisible yet immensely powerful, surges and twists as the star pulsates. Unlike the relatively calm and steady magnetic field of our sun, Mira's magnetism is chaotic, dynamic, and ever-changing. Measurements suggest that its field could be up to 100 times stronger than the sun's. As Mira swells and shrinks, the magnetic field shifts, shaping the powerful stellar wind that streams away from its surface. These winds carry vast amounts of matter into space, gas, dust, and heavier elements forged in the star's fiery interior. Around Mira, astronomers have detected arcs, filaments, and tendrils of this ejected material, forming a shimmering cocoon of cosmic debris. Through these outflows, Mira is seeding the interstellar medium with the ingredients of future stars and planets. Carbon, nitrogen, oxygen, the very elements that compose life itself, are being returned to the galaxy. The tail of material behind Mira stretches astonishingly far, over 13 light-years across, a glowing trail that marks its motion through space. In a sense, the star is writing its own eulogy in light and dust, leaving behind the raw materials from which new worlds may one day form. Determining how fast Mira rotates adds yet another layer of mystery. Estimates suggest it may take several hundred days for the star to complete a single turn, though uncertainty remains high. Its pulsations, its binary companion, and its evolving structure make precise measurements difficult. Yet understanding this rotation is crucial, for it offers insight into the tangled relationship between magnetism, mass loss, and the internal dynamics of aging stars. Mira's binary companion, a faint white dwarf known as Mira B, orbits at a distance comparable to the span between our Sun and Pluto. The two stars engage in a delicate cosmic dance. Material from Mira's outer layers flows toward its companion, creating a bridge of gas and plasma. Over time, Mira B's gravity captures this material, like forming an accretion disk and occasionally producing bursts of ultraviolet radiation. The pair illustrates the complex interplay of death and renewal that characterizes binary star systems, where one star's decline can feed another's activity. Today, Mira stands as a textbook example of a star on the asymptotic giant branch, a brief, unstable stage near the end of stellar evolution. It is shedding its mass at an astonishing rate, losing roughly the equivalent of one Earth every 7 years. This process cannot last forever. In time, the pulsations will cease, and Mira's outer layers will drift away completely, forming a planetary nebula, a glowing bubble of gas illuminated by the remaining core. What remains will be a white dwarf, a dense, cooling ember roughly the size of Earth, but with a mass comparable to the Sun. It will fade over billions of years, growing colder and dimmer until it disappears entirely. Astronomers estimate that Mira is about 6 billion years old, older than our Sun by nearly 1.5 billion years. Its long life and current decay make it a window into our own future. For one day, billions of years from now, our Sun will follow the same path, expanding, reddening, and pulsating before shedding its outer skin into space. Studying Mira is, in a sense, studying destiny. Even now, with every pulse and flare, Mira reminds us of the impermanence woven into the cosmos. It is a dying star, yes, but not a silent one. Through its instability, it speaks of transformation, of renewal, and of the continuous recycling of matter that gives rise to new generations of stars. Each shimmer of its light across the night sky carries a message billions of years in the making, that endings in the universe are never final, only the beginnings of something new waiting to be born. However, its journey is far from over. In fact, what lies ahead for Mira is a chapter of breathtaking transformation, one that marks both an ending and a new beginning in the cosmic cycle of life and death among the stars. Astronomers watching this ancient beacon of light know that Mira's current brilliance is a fleeting act in a much grander celestial performance. Soon, the great red giant will begin to shed its outer layers, a process both violent and mesmerizing. As Mira continues to burn through the last reserves of its nuclear fuel, it will grow increasingly unstable. Each pulsation, once a gentle rhythm of expansion and contraction, will become more erratic, more forceful as the star struggles to maintain balance against the inevitable pull of gravity. Then, in a magnificent finale, Mira will cast vast amounts of gas and dust into space, forming an immense, glowing cocoon known as a planetary nebula. This will be one of the universe's most stunning spectacles. The dying star, surrounded by shells of luminous gas, will appear to blossom like a cosmic flower, its colors shifting through ethereal blues, pinks, and violets. The nebula's glow will come from the heat of the star's now exposed core, a brilliant ember left behind after the outer layers are expelled. That remnant will shrink and compress into a white dwarf, a dense, Earth-sized core containing nearly all the mass of the original star. A white dwarf may sound small and quiet, but it represents one of nature's most extreme states of matter. A teaspoon of it would weigh several tons. Over billions of years, that remnant will slowly cool, fading into obscurity, a dark, cold, stellar corpse adrift in the silent sea of space. This is Mira's fate, but it is also ours. Our own sun, in roughly 5 billion years, will undergo a similar transformation, turning the familiar solar system into a vastly altered place. Yet Mira's story is not just one of death. It is also about renewal. Each puff of gas it releases, each particle it contributes to the interstellar medium, becomes part of a much larger story, one where old stars die so that new ones may form. The carbon, oxygen, and other heavy elements ejected by Mira will someday drift into clouds of gas and dust that will collapse to form new stars, new planets, and perhaps even new life. Mira, or Omicron Ceti as astronomers call it, is one of the most closely studied variable stars in the night sky. Its light waxes and wanes in a cycle lasting about 11 months, a rhythm so regular that ancient astronomers once thought it was a divine pulse, the heartbeat of the heavens themselves. During its bright phase, Mira can shine so intensely that it becomes visible to the naked eye, only to fade months later until it nearly disappears from view. This rhythmic transformation, visible across centuries, continues to captivate scientists and stargazers alike. Modern observations have revealed that Mira is not alone. It is part of a binary system, accompanied by a smaller, hotter companion that orbits at a distance. Together, these two stars create a dance of light and matter that stretches across space. The red giant's immense stellar winds form a tail, an extraordinary stream of ejected material trailing behind it for nearly 13 light years. This tail glows faintly in ultraviolet light, a reminder that even in its waning days, Mira continues to give back to the cosmos. Astronomers estimate that Mira will remain in its current pulsating phase for anywhere between 100,000 and 1 million years, a blink of an eye in cosmic terms. Throughout this time, it will continue to lose mass through its powerful stellar winds, gradually revealing its inner core. Every wisp of gas carried away by these winds enriches the surrounding interstellar medium, seeding it with the ingredients of future worlds. In many ways, Mira is a time machine. By studying it, astronomers can look into our sun's future. They can witness firsthand the processes that will eventually transform our solar system. When our sun swells into a red giant, Mercury and Venus will likely be engulfed, and Earth itself may be scorched or consumed. Beyond that fiery chaos, the sun's dying breath will send its own gases out into space, creating a planetary nebula, a fleeting, final beauty before it settles into the quiet existence of a white dwarf. Observing Mira allows scientists to test and refine models of stellar evolution, those intricate equations and computer simulations that attempt to describe how stars live and die. Its pulsations, measured with increasing precision, act like a window into its interior, revealing the turbulent convection currents and nuclear reactions taking place deep within. By comparing its behavior to theory, astronomers can piece together a more complete understanding of how stars evolve and how the elements forged in their hearts spread throughout the universe. And so Mira continues its journey, immense, unstable, luminous, and doomed. Each flicker of its light is both a farewell and a promise to the star it once was, and a promise that its remains will one day help build new stars, new systems, and perhaps new life. In watching Mira, we are not merely observing a distant point of light. We are witnessing the story of cosmic continuity, the grand cycle of creation and destruction that binds every star, every planet, and every living thing together across time and space. Additionally, detailed spectroscopic observations have allowed astronomers to probe the chemical composition of Mira's atmosphere, uncovering a rich tapestry of elements that serve as fingerprints of its age and the nuclear processes occurring deep within its core. By analyzing these spectral lines, scientists can trace the fusion reactions powering the star, providing vital clues about its evolutionary stage. When this chemical data is combined with precise measurements of Mira's rate of mass loss, the slow shedding of material from its outer layers, researchers can forecast the star's future with remarkable accuracy. Such predictions suggest that Mira may eventually transition into a planetary nebula, leaving behind a dense, cooling white dwarf at its heart, a silent remnant of a once brilliant star. Mira, also cataloged as Omicron Ceti, is not merely a static point of light in the night sky. It is a stellar marvel, a long-period variable star whose luminosity dances across a staggering range. Its pulsation cycle spans approximately 332 days, during which its brightness can increase by nearly 1,000-fold, transforming it from a faint glimmer barely detectable by the naked eye into one of the most prominent stars in its constellation. This dramatic oscillation is a direct consequence of its status as a red giant approaching the final chapters of its stellar life. As Mira consumes the last of its nuclear fuel, it undergoes rhythmic expansions and contractions. When the star swells, its outer layers cool and thicken, absorbing and scattering light, which causes the star to dim. Conversely, as it contracts, the surface heats up, the outer layers become more transparent, and the star shines with renewed brilliance. The driving force behind this pulsation lies in the behavior of helium in the star's atmosphere. When helium atoms ionize, they trap energy within the star, causing the outer layers to expand. As the helium recombines with electrons, the stored energy is released, prompting contraction. This cyclical process repeats over the course of nearly an entire year, producing the striking rhythmic changes in brightness that have fascinated astronomers for generations. Beyond these internal pulsations, Mira is actively shedding its outer envelope, creating an intricate shell of gas and dust that interacts with its light. This circumstellar material can both enhance and diminish the apparent brightness of the star, adding an additional layer of complexity to the cosmic spectacle. The interplay of internal dynamics and evolving surroundings turns Mira into a living laboratory for studying stellar physics, offering a vivid illustration of the life cycle of stars. At its maximum, Mira can reach a magnitude of about 3, easily visible to observers in dark skies without optical aid. At its dimmest, it fades to around magnitude 9 or 10, necessitating a telescope for detection. The sheer scale of this variation, nearly 10 magnitudes, underscores the star's extraordinary nature. For astronomers, tracking these fluctuations is more than an observational curiosity. It provides crucial data about the internal mechanisms of red giants and the forces that govern stellar evolution. Each cycle, each rise and fall in brightness, tells a story about the balance between gravity, pressure, and energy transport within the star's interior. Mira's behavior is not merely a matter of routine repetition. While the general pattern is remarkably consistent, careful monitoring has revealed subtle variations in the timing and amplitude of its pulsations, often shifting by a few days. These minor deviations hint at the complex interplay of processes within the star's atmosphere and core, reflecting changes in density, temperature, and energy flow. By studying these nuances, astronomers gain a window into the later stages of stellar life, offering tantalizing glimpses into what the distant future may hold for our own sun. The star's name, derived from Latin to signify wonderful or astonishing, is a fitting tribute to its remarkable character. Its long-period pulsations have inspired a whole category of stars, known as Mira variables, named after this very star. These stars share the traits of extended cycles and extreme variability, making them valuable cosmic laboratories for understanding the interplay of astrophysical forces over time. Mira's cycle, stretching nearly an entire Earth year, provides astronomers with a predictable yet endlessly fascinating canvas to study the physics of stellar pulsation, energy transfer, and atmospheric opacity. Size changes accompany the luminosity fluctuations, with Mira expanding and contracting dramatically throughout its cycle. At its dimmest, the star contracts to roughly 400 times the radius of the Sun, while at its peak it swells even further, creating a colossal sphere of incandescent gas. This expansion and contraction are not merely cosmetic. They are deeply entwined with the star's temperature, opacity, and brightness variations. Each pulsation is a tangible manifestation of the internal tug-of-war between gravity pulling inward and pressure pushing outward, with helium ionization acting as the metronome of this cosmic rhythm. In its ongoing evolution, Mira is shedding material into the surrounding space, gradually enriching the interstellar medium with heavier elements forged in its core. This process will eventually shape the formation of new stars and planetary systems, demonstrating how, even in its twilight, Mira contributes to the cycle of cosmic creation. For stargazers, the sight of Mira rising to brilliance and fading to near invisibility is more than a visual spectacle. It is a reminder of the transient yet cyclical nature of the universe, a celestial performance that blends physics, chemistry, and time into a mesmerizing display of cosmic artistry. However, as it brightens, the star undergoes a dramatic transformation, swelling to an immense size that can reach up to 700 times the diameter of our Sun. To grasp the enormity of this expansion, imagine placing this star at the very center of our solar system. Its outer layers would stretch far beyond the orbit of Mars, engulfing regions that we typically associate with the inner planets. This remarkable fluctuation in size is intimately tied to the star's changes in brightness. When the star expands, its outer layers cool down and emit less light, causing the star to appear dimmer in the night sky. Conversely, as it contracts, its surface heats up, intensifying its luminosity. This rhythmic pulsation is driven by changes in the opacity of the star's outer layers, producing a steady, almost hypnotic cycle of expansion and contraction. The extreme variability of this star, known as Mira or Omicron Ceti, offers astronomers a rare window into the late stages of stellar evolution. As a red giant approaching the end of its life, Mira serves as a living laboratory, revealing clues about what awaits our own sun billions of years in the future. Its pulsations unfold over roughly 330 days, a period during which its brightness waxes and wanes so dramatically that at its peak, it is visible without any optical aid, while at its faintest, even a telescope is required to detect it. This variability does not merely offer a spectacular cosmic display. It has profound effects on the surrounding environment. As Mira expands and contracts, it sheds enormous quantities of material into space, generating a stellar wind far more intense than anything produced by our sun. Over the course of a decade, the star loses a mass equivalent to that of the Earth. This expelled matter trails behind the star in a vast comet-like tail stretching an astonishing 13 light years, forming a structure rich with complex molecules and elements. These materials enrich the interstellar medium, seeding future generations of stars and planets, and making Mira a critical agent in the cosmic recycling process. The pulsations also send shock waves through the star's extended atmosphere. These waves heat the surrounding gas, causing it to glow and producing intricate structures observable in ultraviolet light. The resulting environment provides a unique natural laboratory for astronomers to study the life cycles of stars like our sun. Mira's constant transformation from a swollen, cool red giant to a contracted, luminous powerhouse offers essential data on stellar physics and the mechanisms driving mass loss in aging stars. Modern astronomers employ an array of observational techniques to track Mira's variability. Visual monitoring remains surprisingly effective. Both professional and amateur astronomers regularly measure its brightness against nearby reference stars, constructing detailed light curves that map the star's luminosity over time. For greater precision, photometry uses specialized instruments to quantify the star's light across various wavelengths, revealing subtle fluctuations in brightness and temperature that are invisible to the naked eye. Spectroscopy adds another layer of understanding by analyzing the star's spectrum to determine changes in temperature, size, and chemical composition throughout its pulsation cycle. Long-term observation programs spanning both ground-based observatories and space telescopes have been indispensable in piecing together Mira's behavior. Continuous monitoring allows astronomers to refine models of stellar pulsation and understand the physical processes governing these dramatic transformations. Mira belongs to a broader class of stars known as long-period variables, with its specific subgroup called Mira variables, serving as prototypes. Stars like Chi Cygni in Cygnus and Arcturus in Leo exhibit similar pulsating behaviors, though each with unique rhythms, brightness ranges, and color transformations. These stars, often red giants nearing the end of their life cycles, expand and contract in a cosmic rhythm that encodes information about stellar structure, evolution, and eventual fate. Historical observations reveal that Mira's variability has fascinated humans for centuries. First documented in the late 16th century by David Fabricius, it was initially thought to be a new star appearing and disappearing in the night sky, earning the Latin name meaning wonderful or astonishing. Over time, careful observation demonstrated that this star was not a transient phenomenon, but a variable star with a remarkably regular cycle. By the 19th century, scientists had determined the roughly 11-month pulsation period, firmly establishing Mira as the prototype of long-period variable stars. Recent discoveries have added yet another layer of complexity to this already captivating system. Mira is part of a binary star arrangement accompanied by a much smaller companion known as Mira B, or VZ Ceti. Detected in 1995 using the Hubble Space Telescope's Faint Object Camera, this companion is a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. Despite its diminutive size relative to Mira, the white dwarf exerts a profound gravitational influence. Some of the material expelled from Mira is captured, forming an accretion disk around the companion and creating an intricate cosmic interplay between the two stars. The orbital dynamics of Mira and its white dwarf companion are equally remarkable. Separated by roughly 60 astronomical units, equivalent to about 5,580,000,000 miles, the two stars take approximately 500 years to complete a single orbit around one another. This long-distance celestial waltz allows astronomers to observe how stars at different evolutionary stages interact, offering unprecedented insights into mass transfer, binary dynamics, and the ultimate fate of stars in close companionship. Mira's story is one of constant transformation, both in terms of size and luminosity, and in its interaction with the surrounding cosmos. From its vast expansions that would engulf Mars if placed at the center of our solar system, to the shedding of matter that travels 13 light-years into space, to the gravitational dance with a dense white dwarf companion, Mira exemplifies the complexity, grandeur, and ongoing evolution of the universe. Through meticulous observation and advanced instrumentation, astronomers continue to unravel the secrets of this extraordinary star, using it as a key to understand not only the life cycles of red giants, but also the ultimate destiny of stars like our own sun. However, their orbital path is far from a perfect circle. Instead, it is highly elliptical, meaning the distance between Mira and its companion constantly changes as they trace their centuries-long dance through space. Completing one full orbit in roughly 5 centuries, these two stars experience dramatic swings in proximity. At the closest point, known as periastron, they approach within just 40 times the distance from Earth to the Sun, a remarkable closeness given their immense sizes. Conversely, at apastron, their separation can widen to nearly 100 times the Earth-Sun distance, illustrating the extreme stretches of their orbital journey. This fluctuating distance profoundly influences the interactions between the stars. Mira, a red giant in the twilight of its life, continually loses mass through powerful stellar winds. Some of this expelled material is gravitationally captured by its smaller, hotter companion, believed to be a white dwarf. The changing gap between the stars modulates the intensity and dynamics of this mass transfer, resulting in a celestial relationship that is intricate, dynamic, and ever-evolving. Mira, also cataloged as Omicron Ceti, presents a vivid example of the life cycle of evolved stars. Its companion, the compact white dwarf, orbits along the elongated trajectory, occasionally drawing in the outer layers of Mira to form an accretion disk around itself. This exchange of material triggers bursts of energy and light. Periodically, the white dwarf brightens suddenly as it consumes the accumulated matter from Mira, events astronomers call dwarf nova outbursts. These eruptions dramatically alter the system's overall luminosity, making the binary a spectacular and unpredictable beacon in the cosmos. The relationship between Mira and its companion offers a rare observational window into stellar evolution and mass transfer in binary systems. Mira's eventual fate is to shed enough mass to become a white dwarf itself, while its companion may undergo further energetic events as the system continues to evolve over thousands of years. Observing this process allows astronomers to trace the long-term consequences of binary interactions on stellar development. Mira A, the primary star, is not a static presence in the sky. It pulsates rhythmically, expanding and contracting with brightness changes that can be observed over hundreds of days. The gravitational influence of Mira B plays a crucial role in shaping these pulsations, subtly distorting the red giant's shape and affecting its internal energy distribution. As a result, Mira A's evolution is accelerated compared to what it would experience in solitude, with the companion's presence intensifying its mass loss process. The two stars' orbital dance also sculpts the surrounding space in intricate patterns. As material flows from Mira A, the orbital motion of the stars weaves this gas and dust into spiral formations, creating a dynamic environment that captures the imagination of astronomers. These structures provide a tangible record of stellar interactions, revealing how mass transfer and gravitational interplay shape the evolution of binary systems over centuries. Furthermore, Mira B's accretion of material from Mira A adds layers of complexity to the system's variability. The companion's influence alters the distribution of gas and dust, affecting how light from Mira A is scattered and absorbed, which in turn contributes to the star's distinctive changes in brightness. The combined effects of orbital motion, pulsation, and mass transfer create a celestial choreography that is intricate and continually evolving, offering profound insights into the life cycles of stars. Located roughly 300 light-years from Earth, the Mira system is a striking example of stellar partnership. The two stars orbit each other in a cycle lasting nearly 5 centuries, an orbit so extended that astronomers must rely on data spanning multiple generations to fully grasp its dynamics. On average, they remain about 100 times the Earth-Sun distance apart, yet their gravitational interplay produces phenomena that dwarf what we might expect from solitary stars. Mira A's pulsations are pronounced enough that at peak luminosity it can sometimes be seen with the naked eye, while at dimmest it fades almost entirely from view. Meanwhile, Mira B, much smaller but intensely hot, captures material from these pulsations, forming a luminous accretion disk and triggering intermittent flares. These interactions create a light show that not only fascinates astronomers but also provides a natural laboratory for studying processes such as mass transfer, stellar wind, and the evolution of red giants and white dwarfs. The stellar wind from Mira A, extending an astonishing 13 light-years into space, is shaped in part by the companion's gravitational influence. This remarkable phenomenon illustrates how binary systems can redistribute material across vast distances, sculpting the environment around evolving stars in ways that are both intricate and visually stunning. Through the Mira system, astronomers gain a deep understanding of how stars influence each other, how mass flows through space, and how binary interactions can dramatically accelerate or alter the life cycles of the stars involved. In essence, Mira and its companion embody the cosmic complexity of binary evolution. Their centuries-long orbital waltz, the periodic exchange of stellar material, and the dramatic variations in brightness all combine to paint a vivid portrait of stellar life in motion. This system is more than a simple pairing of stars. It is a dynamic laboratory where the forces of gravity, nuclear fusion, and stellar wind come together to tell a story of change, interaction, and the relentless passage of cosmic time. Furthermore, examining Mira and its stellar companion opens an extraordinary window into the later stages of life for stars bound in binary systems. As Mira A continues its evolution, it is destined to become a white dwarf, just like its partner, offering astronomers a rare glimpse into the ultimate fate awaiting countless binary stars scattered throughout our galaxy. Understanding this process is far from trivial. It is essential for refining models of stellar evolution and for illuminating the complex life cycles of stars, which are among the most fundamental processes shaping the cosmos. Mira, a truly exceptional star within the Milky Way, leaves an unforgettable imprint across the galaxy as it speeds through interstellar space. Its trail, a staggering 30 light-years long, stretches across the heavens and is composed of carbon, oxygen, and other elements that Mira sheds as it races at phenomenal speeds, roughly 300,000 miles per hour. Unlike the stars we see twinkling serenely in the night sky, Mira is in motion, plowing through the thin gas and dust that pervade the galaxy. This interstellar medium acts like an invisible wind, sculpting the material the star ejects into a luminous, twisting tail that resembles the wake left behind by a ship cutting through ocean waters. This expelled matter is not mere cosmic detritus. It represents Mira's outer layers being stripped away as it approaches the final chapters of its life. Mira is a red giant, swelling and pulsating as it nears the end of its existence, losing mass at a prodigious rate, enough each year to form an Earth-sized planet. The turbulent trail left behind is a swirling, eddying spectacle, revealing the hidden dynamics of stellar winds and the subtle interplay between stars and the surrounding interstellar medium. Each twist and curl in the trail provides astronomers with vital clues about how matter behaves under these extreme conditions. The scale of Mira's trail is almost beyond comprehension. Spanning an astonishing 13 light years, equivalent to roughly 123 trillion kilometers, it dwarfs familiar distances within our own solar system, stretching some 20,000 times the space from the Sun to Pluto. This awe-inspiring phenomenon was first observed in 2007 through the ultraviolet eyes of the Galaxy Evolution Explorer Space Telescope, known as GALEX. Its discovery offered scientists an unprecedented opportunity to witness firsthand the life cycle of a dying star and its contributions to the galactic ecosystem. Mira's trail is not merely an extraordinary visual, it is a cosmic engine of creation. The carbon, oxygen, and other elements it deposits into space enrich the interstellar medium, becoming potential building blocks for future stars, planets, and even the raw ingredients of life. This ongoing process underscores the intricate interconnectedness of the universe, where the death of one star sows the seeds of countless others. While Mira's tail is unique among stars, comets offer a parallel in their spectacular tails. Comets possess two distinct features, a dust tail and an ion tail. The dust tail, composed of rock and ice particles released as the comet approaches the sun, forms a curved path reflecting sunlight, stretching millions of kilometers behind it. The ion tail, comprised of electrically charged gases, is propelled by the solar wind and can reach velocities of up to 1,000 kilometers per second, forming a straight bluish streak extending directly from the sun. The varying composition and speed of these tails create the dazzling displays that have inspired observers throughout human history. Mira, officially cataloged as Omicron Ceti in the constellation Cetus, shares some of these dynamic traits, but on a vastly larger and more impactful scale. Traveling at 130 kilometers per second, it sheds material that has been accumulating over tens of thousands of years, creating a tail visible only in ultraviolet light. Unlike a comet or the fleeting debris of a supernova, Mira's wake is persistent, forming a colossal corridor of carbon, oxygen, and other heavy elements critical to the formation of new celestial structures. The discovery of Mira's trail highlights the extraordinary power of space-based telescopes like GALEX, which can detect ultraviolet light blocked by Earth's atmosphere. Through these observations, astronomers have been able to witness a star leaving a tangible mark on the galaxy, a vivid testament to the dynamic processes of stellar evolution and the mechanisms by which stars shape their cosmic environments. Mira's journey is a spectacle of motion, mass loss, and cosmic creation. As it speeds through the galaxy, the interaction of its expelled material with the interstellar medium forms bow shocks, turbulent wakes, and swirling eddies, offering a rare glimpse into the life of an aging red giant. This phenomenon provides scientists with an unparalleled laboratory for understanding the distribution of elements across the Milky Way, tracing the continuous cycle of stellar birth, death, and rebirth. In every kilometer of its trail, Mira narrates the story of stars as architects of the universe, seeding the galaxy with the ingredients for future generations of stars, planets, and perhaps life itself. The remarkable discovery and ongoing observation of Mira's trail not only expand our understanding of stellar physics, but also allow us to witness the tangible legacy of a star in motion. It stands as one of the most extraordinary and instructive examples of how individual stars leave indelible marks upon the cosmos, ensuring that even in their final stages, they continue to shape the universe around them. Furthermore, the intricate shape and complex structure of Mira's trail reveal an extraordinary amount of information about the star's motion through the galaxy and its dynamic interactions with the interstellar medium. The bow shock at the forefront of the trail, formed as the star compresses gas and dust in its path, acts like a cosmic anvil, offering astronomers critical clues about the density, temperature, and chemical composition of the space that stretches between stars. Every ripple, every turbulence in this stellar wake carries a hidden story about how stars move, collide with, and shape the material around them. Studying Mira's trail is more than just mapping a star's path. It is a window into the life cycles of sun-like stars and a preview of their eventual fates. Mira is a red giant, teetering on the edge of stellar retirement, and its trail is a glowing breadcrumb, documenting its journey across the galaxy. The wake it leaves behind is not mere debris. It is a detailed chronicle of the processes that unfold in the late stages of a star's life. By analyzing this trail, astronomers gain insight into the mechanisms of stellar aging, the physics governing mass loss, and the ways dying stars recycle matter back into the cosmos, enriching the interstellar medium with the very elements that seed new stars and planets. Mira's ejected material forms a breathtaking cosmic stream that extends over 13 light years, a remarkable distance that underscores the sheer scale of the phenomenon. As it races through space at approximately 87 meters per second, the star sheds its outer layers, expelling carbon, oxygen, and heavier elements forged deep within its core. This ejected matter does not simply vanish. It forms a turbulent, twisting wake that mixes with the interstellar gas and dust, infusing it with the essential components for the next generation of stars. The process, known as stellar enrichment, is a vital contributor to galactic evolution, gradually increasing the metallicity of the interstellar medium and altering its chemical composition over time. The high-speed journey of Mira through the galaxy also generates shock waves that have the power to trigger the birth of new stars. As the stellar material collides with surrounding gas clouds, the compression can initiate the gravitational collapse necessary to form new stellar bodies. Mira, therefore, is not merely a dying star leaving behind a trail. It is a cosmic catalyst, chemically and dynamically shaping the ongoing evolution of our galaxy. Its role in this cosmic choreography highlights the intricate feedback loops that govern the life and death of stars, showing how individual stellar events can ripple through the broader galactic environment. Mira is located in the constellation Cetus, roughly 400 light years from Earth, and its extraordinary behavior stems from its status as a pulsating variable star. Over a period of roughly 11 months, Mira alternately swells and contracts, sending powerful shock waves through its atmosphere. These pulsations, combined with the star's diminished surface gravity, allow vast amounts of material to escape, driven outward by radiation pressure and the formation of dust grains in the star's cooling outer layers. These dust grains act as miniature sails, catching the star's light and carrying gas into interstellar space, contributing further to the creation of the star's spectacular tail. Every year, Mira loses roughly 1/10,000,000th of the sun's mass. Though this may seem negligible, it amounts to a staggering quantity of matter when considered over thousands of years. In fact, the material expelled annually could accumulate into an Earth-sized planet in just 10,000 years. The sheer scale of this mass loss forms a trail that stretches over 13 light years, creating a glowing, elongated wake of gas and dust behind the star. The speed at which Mira ejects this material is astonishing, reaching nearly 300,000 kilometers per hour, about 1/4 the speed of light, demonstrating the incredible forces at play in the late stages of stellar evolution. Mira's trail is not uniform. It is a living, breathing record of the star's variability and its interaction with the galaxy. The ultraviolet radiation from the star ionizes the surrounding gas, causing portions of the trail to glow, while the star's speed generates a bow shock at the leading edge, compressing the interstellar medium and influencing the shape of the wake. The variability of Mira, cycling approximately every 330 days, also affects the density, temperature, and composition of the ejected material. During brighter phases, hotter and more energetic particles are expelled. During dimmer phases, the material is cooler, resulting in alternating regions of density and temperature along the trail. In essence, Mira's journey is a dynamic testament to the life of stars, the recycling of cosmic material, and the ever-changing nature of our galaxy. Its tail stretches across space like a glowing river of matter, each pulsation, shockwave, and ejection revealing the complex interplay of forces that govern stellar evolution. This red giant, racing at nearly 500,000 kilometers per hour, leaves a trail not just of matter but of knowledge, illuminating the processes by which stars die, enrich the cosmos, and contribute to the ongoing story of the universe. Furthermore, the rhythmic pulsations of Mira are far more than a mere stellar heartbeat. They act as the engine that continuously drives the ejection of material from the star's outer layers. Without these periodic fluctuations, the star would be incapable of replenishing the immense trail of gas and dust it leaves in its wake, a trail that is constantly sculpted and stretched by Mira's rapid journey through the interstellar medium. The variability of Mira is therefore not simply a contributing factor in this cosmic spectacle. It is a central force, a fundamental driver in both the creation and ongoing maintenance of its extraordinary stellar wake. The dynamic interaction between Mira and its companion star further amplifies this phenomenon, creating one of the most visually striking examples of stellar mass loss in our galaxy. Mira, a red giant approaching the final stages of its life, naturally sheds its outer layers in a process that generates a steady stellar wind. Yet the presence of a smaller, denser companion, likely a white dwarf, dramatically intensifies this effect. As the two stars orbit each other, their mutual gravitational pull causes Mira to pulsate more violently, accelerating the rate at which it expels matter into space. These interactions sculpt the escaping material into intricate patterns. The gravitational influence of the companion twists the expelled gas and dust into spiraling formations, while its motion through this ejected material produces a bow shock akin to the wave formed by a ship cutting through water. This bow shock compresses and heats the gas, enhancing its visibility and creating a trail that is both longer and more luminous than Mira could produce alone. As Mira propels itself at extraordinary speeds through space, it leaves behind a vast trail of processed stellar material, a cosmic ribbon stretching over 13 light-years. This tail is composed of particles that have cooled to astonishingly low temperatures, nearing that of the cosmic microwave background, around 3 degrees above absolute zero. Despite their frigid state, these particles are not entirely inert. They still retain minute quantities of energy, permitting molecular interactions and even the potential for the formation of new stars in the distant future. Along this trail, astronomers can observe not only the dramatic redistribution of elements, but also the subtle fingerprints of stellar evolution in action, revealing how stars interact with and shape their galactic environment, even in the twilight of their lifespans. The composition of Mira's tail evolves dramatically with distance from the star. Close to Mira, the trail is rich with carbon-laden dust and molecules expelled from the star's pulsating outer layers. As one moves further along the trail, these materials gradually intermingle with the surrounding interstellar medium, incorporating abundant hydrogen and other elements, producing a chemically diverse environment. At the farthest reaches, the trail becomes increasingly molded by interactions with interstellar gas and radiation. Shock waves generated by Mira's high-velocity passage compress the medium, triggering new molecular formations, while ultraviolet radiation from nearby stars can break apart original molecules, further altering the chemical composition. The result is a vast, evolving chemical tapestry that chronicles both Mira's journey and the dynamic processes that shape the interstellar medium, highlighting the ongoing enrichment of our galaxy. The morphology of Mira's trail is as remarkable as its composition. Its leading edge forms a bow shock, a dramatic arc where the star's rapid motion compresses interstellar gas and dust. Behind this arc, the trail becomes a turbulent wake filled with swirling filaments and eddies, segmented clumps, and knots of material that likely correspond to episodic increases in Mira's mass loss. Some scientists suggest that these segments act as a cosmic logbook, recording the star's movement through varying regions of the galaxy. The trail gradually widens into a cone-like structure as the expelled material interacts with and disperses into the surrounding medium. In these ways, Mira's trail offers a unique window into both the star's history and the broader mechanisms that govern stellar feedback within galaxies. Mira, located in the constellation Cetus, has been leaving behind this extraordinary trail for roughly 30,000 years. Traveling at an impressive speed of 130 kilometers per second, the star continuously sheds material, creating a tail that stretches 13 light-years, a testament to the dynamic and interconnected nature of the galaxy. Friction with the interstellar medium compresses gas ahead of Mira, forming a bow shock analogous to the wake of a ship, while the expelled material stretches behind, enriched with heavy elements that will later contribute to new stars and planetary systems. Observations using ultraviolet telescopes, such as NASA's Galaxy Evolution Explorer, have revealed this trail with remarkable clarity, granting astronomers a window into the life cycle of stars and their role in redistributing elements throughout the cosmos. Mira is also a celebrated variable star, formerly known as Omicron Ceti, whose brightness fluctuates dramatically over a period of approximately 11 months. At its peak, it can shine as a bright third magnitude star, easily visible to the naked eye, while at its dimmest, it fades to a 10th magnitude, requiring binoculars or a small telescope to observe. This extreme variability, combined with its distinctive trail, makes Mira a prime target for both professional and amateur astronomers. Careful monitoring over several months allows observers to construct detailed light curves, capturing the full range of Mira's pulsations. These observations provide insights into the mechanisms driving stellar variability and contribute to broader scientific understanding. Observing Mira requires patience, preparation, and a keen eye. Located near the neck of the whale-shaped constellation Cetus, it is most visible in the northern hemisphere during the autumn and winter months. By comparing Mira's brightness to nearby stars of known magnitude and recording these observations over time, enthusiasts can create personal data sets that chart the star's changing luminosity. For those equipped with telescopes, digital imaging can produce precise measurements of brightness fluctuations, enabling meaningful contributions to ongoing research. The star's Latin name, meaning wonderful or astonishing, perfectly encapsulates the awe-inspiring nature of this variable giant. At its brightest, Mira transforms the night sky into a showcase of stellar power and evolution, a living testament to the cosmic forces that sculpt our universe. This extraordinary star and its immense trail stand as a vivid reminder of the life cycles of stars, the interplay of gravity, motion, and stellar physics, and the intricate dance between a star and its environment. Mira's journey through space, the pulsations that drive its mass loss, the bow shock it generates, and the chemical evolution of its 13 light-year-long tail together form one of the most remarkable and visually compelling phenomena in the night sky, captivating both astronomers and casual stargazers alike. However, when its light dims, Mira's brilliance recedes dramatically, dropping to a faint magnitude of roughly 9 or 10. At this level, it becomes invisible to the unaided eye, requiring binoculars or a small telescope to witness its glow. This remarkable fluctuation in brightness is part of what makes Mira such a captivating target, appealing both to novice stargazers eager to spot their first variable star and to seasoned observers drawn to the rhythms of the heavens. For those who wish to study Mira's cyclical changes in a systematic way, a detailed star chart of the constellation Cadus is indispensable. By comparing Mira to neighboring stars of known brightness, observers can estimate its current magnitude, track its gradual brightening and dimming, and begin to appreciate the subtle nuances of stellar variability. Many astronomers find that using a dim red flashlight while consulting charts preserves night vision, allowing extended periods of careful observation without losing sensitivity to faint celestial objects. While it is not strictly necessary, keeping a meticulous log of observations over weeks and months can allow amateur astronomers to construct their own light curve, charting Mira's 11-month pulsation cycle. This hands-on approach fosters a tangible connection to the cosmos, revealing a universe far from static, a realm where stars pulse, evolve, and leave traces of their existence across space. Mira itself, situated in the constellation Cetus, is remarkable not just for its oscillating luminosity, but also for the vast trail it carves through space. Stretching an astounding 13 light-years behind it, this wake is imperceptible to the naked eye and even to standard backyard telescopes. Its discovery relied on the advanced sensors of the Galaxy Evolution Explorer satellite, which observes in ultraviolet light, unveiling features invisible to traditional optical instruments. Although amateur astronomers cannot directly witness this ultraviolet trail, the star's shifting light is enough to offer a window into its celestial story. Mira is a classic variable star, a pulsating red giant whose brightness waxes and wanes over a period of about 11 months. At its peak, it occasionally shines brightly enough to be seen without optical aid, glowing with a subtle reddish hue against the night sky. During its fainter phases, it slips beyond unaided vision, requiring binoculars or a small telescope to track its presence. For those willing to invest patience and a few simple instruments, observing Mira over multiple months can produce personal light curves, capturing the cycle of expansion and contraction that drives its luminosity changes. This long-term observation transforms casual stargazing into an immersive scientific experience, connecting observers with the ever-changing dynamics of stars and the broader cosmic environment in which they exist. Although the star's radiant trail remains hidden from amateur telescopes, the story of Mira and its 13 light-year wake offers a vivid reminder of the invisible processes shaping the galaxy. It urges observers to consider the unseen effects of stellar motion and evolution, encouraging a mindset that stretches beyond the immediately visible. Space-based observatories have been crucial in revealing the intricacies of Mira's behavior and the extent of its trail. In 2007, the Galaxy Evolution Explorer, also known as GALEX, captured ultraviolet light, revealing the astonishing 13 light-year tail streaming behind Mira. This instrument highlighted how the star continually leaves a wake of material in its path, illuminating interactions with the surrounding interstellar medium. Hubble's high-resolution optics have allowed astronomers to study Mira's variable surface, including the turbulent structures of its outer layers, providing insights into mass loss and the formation of circumstellar dust. Meanwhile, the Spitzer Space Telescope, observing in infrared, has pierced the surrounding dust to reveal temperature fluctuations and atmospheric composition. Looking forward, the James Webb Space Telescope promises to push these investigations further, potentially uncovering new aspects of the trail and deepening our understanding of how Mira interacts with its galactic environment. Spectroscopy has been central to unraveling Mira's mysteries. By dispersing the star's light into a spectrum, astronomers can decode its chemical fingerprint, identifying elements such as hydrogen, helium, carbon, and oxygen. Variations in spectral lines reveal temperature fluctuations as the star pulsates, expands, and contracts over its 11-month cycle. Moreover, Doppler shifts in these lines allow precise measurements of stellar winds, providing insight into how Mira sheds its outer layers. These layers contribute to the enrichment of the interstellar medium, a fundamental process in the life cycle of stars. Studying Mira's trail presents extraordinary observational challenges. Stretching 13 light-years, roughly 40,000 times the distance from Earth to the Sun, the trail is vast yet tenuous, composed mainly of carbon, oxygen, and other expelled elements. Its diffuse nature makes it invisible to ordinary optical telescopes, necessitating ultraviolet-sensitive instruments aboard space telescopes. Mira's variable brightness further complicates the task, requiring careful timing to capture both the star and the evolving trail. As the star moves through space, new material continuously forms the wake, while older matter disperses, demanding repeated observations to understand its dynamics fully. The trail itself is distinctive, a bow shock-shaped structure, its uniform width and alignment directly linked to Mira's trajectory through space. Spectroscopy confirms its composition, differentiating the trail from nebulae or supernova remnants. Long-term monitoring reveals the trail's evolution, capturing changes in shape, extent, and intensity over time. These observations collectively create a comprehensive picture of Mira's influence on its surrounding environment. Astronomers remain captivated by Mira, and future observations promise even deeper insights. The James Webb Space Telescope is poised to probe the star's dust-enshrouded regions with unprecedented clarity, potentially revealing new details about its structure, composition, and mass loss mechanisms. Each ground-based and space-based observation adds to our understanding, illustrating the complex interplay between a single pulsating star and the vast, ever-shifting tapestry of the galaxy it inhabits. Mira's story, from its flickering light visible through small telescopes to its hidden ultraviolet carved trail spanning 13 light-years, exemplifies the dynamic and interconnected nature of the cosmos, offering both scientists and amateur observers a rare opportunity to witness the rhythms of the universe firsthand. Additionally, long-term monitoring programs that combine the power of both optical and radio telescopes are poised to continue for many years, providing astronomers with an invaluable window into the life of this extraordinary star. Through persistent observation, scientists can track subtle fluctuations in Mira's brightness, charting the intricate rhythm of its pulsation cycle and detecting any shifts in its behavior over time. These sustained studies are not mere exercises in data collection. They are essential for unraveling the complex processes that govern how stars like Mira evolve and how they contribute to the chemical enrichment of the interstellar medium, spreading the building blocks for future generations of stars and planets. Future research may delve even deeper, focusing on Mira's binary companion and the dynamic interactions between the two stellar bodies. High-resolution imaging techniques, combined with detailed spectroscopic observations, promise to illuminate the nature of this stellar partnership, revealing how the gravitational interplay and exchange of material between the stars influences their evolution and behavior. As next-generation telescopes come online, our ability to observe Mira and its astonishing trailing material will be revolutionized. These instruments, equipped with unprecedented sensitivity and remarkable resolution, will allow astronomers to discern finer details than ever before, capturing the subtle features of this intriguing system with extraordinary clarity. With advanced infrared capabilities, these telescopes will pierce through the cosmic veil of gas and dust surrounding Mira, unveiling the full extent of its comet-like tail, which stretches across an astonishing expanse of space. This tail, a record of Mira's past mass loss events, carries a wealth of chemical information. By analyzing its composition with unprecedented precision, scientists will be able to identify the various elements and compounds dispersed into space as the star sheds its material. Such detailed chemical studies provide profound insights into the life cycle of stars and the ongoing enrichment of the interstellar medium. Moreover, enhanced imaging will allow astronomers to observe the tail's evolution in real time, detecting dynamic interactions with the surrounding medium and revealing previously unseen structures within the trail itself. By combining data from multiple next-generation telescopes, both on the ground and in space, scientists will assemble a comprehensive, multi-wavelength portrait of Mira and its environment. This holistic approach will shed light on the physical mechanisms that drive the star's extraordinary behavior and clarify its influence on the surrounding cosmic neighborhood. Mira, also cataloged as Omicron CT, is an aging red giant that plays a remarkable role in shaping its cosmic environment. As it nears the end of its life, the star undergoes a fascinating process of mass loss, expelling vast quantities of gas and dust into space. This outflow is driven by the pulsations and expansion of the star, which continuously ejects its outer layers, forming a stellar wind that carries essential elements such as carbon, oxygen, and nitrogen into the interstellar medium. These elements, forged deep within the star over millions of years, act as the raw ingredients for new stars, planets, and potentially even life itself. The interaction between Mira's stellar wind and the surrounding medium generates a striking bow shock, reminiscent of the wake left by a speeding boat in water. This shock not only compresses and heats nearby gas, but can also trigger the birth of new stars in the region, illustrating how one dying star can spark the formation of many others. Behind the star stretches a trailing tail, more than 2 light-years long, a cosmic river of material that enriches the galaxy with its chemical bounty. Mira's impact extends far beyond its immediate surroundings. Traveling through space at roughly 87 meters per second, it carves a turbulent wake in the interstellar medium, leaving complex structures that include both a bow shock ahead of the star and a trailing wake of gas and dust. The expelled material from Mira enriches the galactic environment, providing essential ingredients for future star formation and contributing to the broader chemical evolution of the galaxy. The star's ultraviolet radiation and the shock waves generated by its wind influence the ionization and heating of the surrounding gas, subtly shaping the dynamics of the local galactic environment. Its binary companion, Mira B, a smaller white dwarf, is deeply affected by the stellar wind from the red giant. Material from Mira accretes onto the companion, creating a complex, gravitationally driven interaction that further sculpts the surrounding gas and dust. This intricate stellar dance not only shapes the immediate environment, but also demonstrates how interconnected celestial systems can be, with each star influencing the evolution of the other and the broader interstellar medium. Over tens of thousands of years, Mira has left a comet-like tail stretching nearly 13 light-years, filled with the carbon, oxygen, and other elements it has expelled. This tail is not static. It interacts with the interstellar medium, forming turbulent wakes and compressed gas regions that may collapse to form entirely new stars. Every year, Mira sheds enough mass to form an object roughly the size of Earth, seeding the galaxy with vital materials for future generations. In this way, Mira acts as a cosmic recycler, ensuring that the elements it forged during its lifetime continue to participate in the galactic cycle of birth, evolution, and death. By observing stars like Mira, astronomers gain invaluable insight into the processes governing stellar evolution, particularly during the final, tumultuous stages of life for red giants. These stars demonstrate how individual stellar objects contribute to the ongoing enrichment of the galaxy, distributing the heavy elements necessary for complex chemistry and even life. Mira's pulsations, mass loss, and interactions with its binary companion illustrate the intricate mechanisms through which stars influence their surroundings, triggering new star formation, sculpting interstellar clouds, and maintaining the dynamic balance of the cosmos. In essence, Mira exemplifies the interconnectedness and continual renewal of the universe. From its pulsating core to its immense trailing tail, from its binary companion to the stars and planets it may help create in the future, this remarkable red giant embodies the dynamic, ever-changing nature of the galaxy. By studying its behavior and environment, scientists are not just observing a single star. They are witnessing the ongoing story of galactic evolution, a tale of creation, transformation, and the ceaseless cycle of cosmic life. Moreover, the final evolutionary stages of Mira-type stars play a crucial role in shaping the visible tapestry of galaxies. As these stars transition into planetary nebula, they create breathtaking displays of color and light that can be observed across immense cosmic distances. Each nebula serves not only as a visual spectacle, but also as a cosmic milestone, marking the life cycle of a star and contributing to the overall luminosity and aesthetic of its host galaxy. Among these stellar marvels, the red giant star known as Mira stands out for its extraordinary journey through space. As Mira travels, it interacts with the interstellar medium in ways that are both dynamic and visually stunning. Moving at incredible speeds, this celestial wanderer plows through the sparse gas and dust that occupy the vast stretches between stars, generating a bow shock reminiscent of the wave that forms at the prow of a ship slicing through water. This shock compresses and heats the surrounding interstellar material, causing it to glow and form a visible arc that leads the star on its path. Behind Mira, the story continues, as a turbulent wake of gas and debris stretches out for an astonishing 13 light-years, creating a cosmic tail reminiscent of a comet's trail. The tail itself is composed of material shed by Mira and interstellar gas that has been swept up and energized by its passage. Within this wake, complex eddies and swirling patterns emerge as Mira's stellar wind collides and mixes with the ambient interstellar gas. These turbulent regions serve as natural laboratories for astronomers, offering invaluable insights into the dynamics of stellar winds, the physical properties of the interstellar medium, and the broader processes that sculpt galaxies over cosmic time. Mira, a variable star residing in the constellation Cetus, moves through the galaxy at a breathtaking velocity of 130 kilometers per second relative to the surrounding interstellar medium. At this speed, the bow shock generated by the star is a spectacular phenomenon, a luminous arc where its high-velocity wind collides with interstellar gas, compressing and heating it to create a visible structure. The wake trailing Mira, extending over 13 light-years, is rich with stellar debris including carbon, oxygen, and other elements expelled from the star itself. Astronomers have coined the term bow shock nebula for this vast comet-like formation, which enriches the surrounding medium and seeds the raw materials for future stars and planets. Observing Mira and its bow shock provides a rare glimpse into the life of an evolved star and the profound effects such objects have on their galactic neighborhoods. The star's intense radiation interacts with surrounding gas clouds, causing them to ionize and glow, creating a vivid nebula. Its powerful stellar wind expels enormous quantities of matter, forming an extended atmosphere that reaches far beyond what one might consider the star's surface. These processes continuously feed the interstellar medium with heavy elements, contributing to the chemical evolution of the galaxy. Mira's influence extends even further when it interacts with other stars or celestial structures. Its binary companion, Mira B, experiences mass transfer as material from Mira's atmosphere flows toward it, forming an accretion disk that further complicates the dynamics of the system. As the star plows through the galaxy, encounters with nebulae or molecular clouds produce dramatic bow shocks that compress and heat the surrounding gas, potentially triggering the birth of new stars. The star's expelled material mixes with the clouds, enriching them with heavier elements and potentially fostering the formation of new molecules and dust grains. Even Mira itself can be affected, as it may accrete some of the denser material it encounters, altering its composition, pulsation patterns, and mass loss behavior. Mira stars, often referred to as long-period variable stars, occupy a unique niche in the cosmic landscape. Unlike stable main-sequence stars such as our Sun, these pulsating red giants experience dramatic changes in brightness and size over periods of hundreds of days. Their most remarkable feature is the prodigious mass loss they undergo. As they expand and contract, they shed vast amounts of material, enriching the interstellar medium with heavy elements and significantly influencing galactic chemical evolution. In contrast, smaller stars like our Sun impact their surroundings more modestly, primarily through the solar wind. Even massive supergiants, which end their lives in explosive supernova, produce abrupt but short-lived changes in their environments. Mira variables, however, leave a subtler yet far more enduring mark. Over millions of years, they gradually disperse their material, creating extended envelopes of gas and dust that can span multiple light years. These envelopes eventually merge with the interstellar medium, supplying essential elements and compounds that will form the next generations of stars and planets, continuing the cycle of cosmic evolution. The journey of Mira is a vivid testament to the dynamic and ever-changing nature of the universe. Even seemingly static stars are constantly in motion, interacting with their surroundings, sculpting space, and seeding future stellar generations. The pulsations, radiation, stellar winds, and turbulent wakes of stars like Mira demonstrate the intricate web of physical processes that drive the evolution of galaxies, highlighting the extraordinary interconnection between individual stars and the grand tapestry of the cosmos. Furthermore, the rhythmic pulsations of Mira stars send ripples through the fabric of space, generating shockwaves that traverse vast cosmic distances. These waves, subtle yet persistent, have the remarkable ability to trigger the birth of new stars within nearby molecular clouds, setting these stars apart from both their smaller, quieter counterparts and the cataclysmic explosions of supernovae. In this way, Mira stars carve out a distinct role within the cosmic ecosystem. They are architects of their stellar neighborhoods, shaping the environment through steady, continuous influence rather than sudden, violent disruption. Mira itself, a singular star that has captured the imagination of astrophysicists for centuries, stands as a testament to the wonder of the cosmos. Known also as Omron Ceti, it was the first star of its type ever documented, earning a place in the annals of astronomy as a celestial pioneer. Its name, derived from Latin to signify wonderful or astonishing, reflects the profound awe inspired in early observers who tracked its dramatic fluctuations in brightness. What makes Mira truly extraordinary is the cyclical nature of its brilliance. And over a period of approximately 332 days, it transforms from one of the brightest points in the constellation Satis to near invisibility, disappearing almost entirely from naked eye view. This extreme variability provides a unique observational laboratory for astronomers, allowing them to study the late stages of stellar evolution with unparalleled clarity. Mira is not merely an isolated curiosity. It has become the prototype for an entire class of stars now known as Mira variables. These stars, typically red giants nearing the end of their lives, shed their outer layers as they pulsate, offering scientists invaluable insights into stellar aging, mass loss, and the enrichment of the interstellar medium with heavy elements. Beyond its rhythmic brilliance, Mira has surprised researchers with a striking feature, a comet-like tail that stretches a staggering 13 light-years behind it as it speeds through space. This immense trail of material has opened new avenues for understanding the interactions between stellar winds and the interstellar medium, turning Mira into a continual source of fascination and study within astrophysics. Mira's significance extends further still. It has shed light on the complex dynamics of binary star systems, with Mira A, the primary star, sharing a gravitational dance with a companion, Mira B. Material from Mira A's stellar wind is drawn toward Mira B, providing a live demonstration of how binary systems exchange mass and influence each other's evolution over time, a scenario that is far from rare in our galaxy. The historical impact of Mira cannot be overstated. Located roughly 300 light-years from Earth, it was first documented as a variable star in the late 16th century by Dutch astronomer David F. Britius. This discovery challenged the long-held belief in the immutability of stars, revealing them as dynamic, evolving entities rather than eternal, unchanging points of light. As the archetype of Mira variables, this pulsating red giant has offered astronomers a crucial window into the final stages of stellar life. Mira variables are characterized by long-period fluctuations, typically lasting from 80 to 1,000 days, with brightness oscillating by several magnitudes. These changes are driven by pulsations in the star's outer layers. As the star expands and contracts, its surface temperature and size shift dramatically, producing the striking variations in luminosity observed from Earth. The study of Mira and similar stars has provided astronomers with powerful tools for modeling stellar interiors and atmospheres more accurately than ever before. Moreover, Mira has deepened our understanding of mass loss in aging stars and its role in cosmic recycling. As it sheds enormous amounts of material, the star enriches the interstellar medium with heavy elements, materials that will eventually become part of new stars, planets, and even life itself. Observations have revealed that Mira loses mass at a breathtaking rate, roughly equivalent to the mass of Earth every 8 years, creating its immense 13 light-year tail. Data from ultraviolet observations, including those from the Galaxy Evolution Explorer spacecraft, have made it possible to study this tail in detail, transforming our understanding of how dying stars distribute matter throughout the galaxy. In every sense, Mira stands as a beacon of astronomical knowledge and a symbol of cosmic wonder. Its pulsations, mass loss, and interactions with the surrounding environment continue to offer profound insights into the life cycles of stars, the dynamics of binary systems, and the ongoing enrichment of the galaxy. Each observation reinforces the extraordinary role that variable stars play in the universe, reminding us that even in the vast, silent expanse of space, stars are not static. They breathe, age, and transform, leaving traces that shape the next generation of celestial bodies. Furthermore, Mira's observations have revolutionized our understanding of how aging stars lose mass, revealing that it is far from a gentle, uniform process. Instead, mass loss in these stellar elders occurs in fits and starts, often erupting in sudden bursts that correlate strikingly with changes in the star's brightness. Each of these ejections throws shells of gas and dust into the surrounding space, forming intricate, concentric layers that act as a detailed historical record, chronicling the star's episodic outbursts over millennia. These shells allow astronomers to literally trace back the star's mass loss events, reconstructing its recent past in a way no other phenomenon permits. Mira, also cataloged as Omicron Ceti, exemplifies this complex behavior. Observations show that as the star pulsates, expanding and contracting rhythmically, shock waves travel through its extended atmosphere, effectively lifting stellar material to heights where the star's gravity can no longer hold it. This remarkable mechanism explains how even relatively cool red giants can shed vast quantities of their outer layers, defying earlier assumptions that only hot stars could undergo significant mass loss. In this way, Mira operates as a living laboratory for astronomers, offering a rare, tangible glimpse into the final chapters of stellar evolution. Situated about 300 light-years from Earth in the constellation Cetus, Mira is a red giant nearing the end of its life cycle. Over a period of approximately 330 days, the star's luminosity fluctuates dramatically. At its peak, it shines brightly enough to be seen with the naked eye, while at its dimmest, it nearly vanishes from view. These pulsations, driven by the cyclic expansion and contraction of the star's outer layers, are not merely aesthetic phenomena. They are deeply informative. By monitoring these brightness variations, astronomers gain insight into the star's internal structure, composition, and the dynamic processes occurring deep within its core. Mira also offers a stark preview of the distant future of our own sun. Sharing a similar mass with our star, Mira illustrates what awaits our solar system in roughly 5 billion years. Its outer layers are being actively expelled, forming an extraordinary tail of material stretching 13 light-years into space. This mass loss phase is pivotal in stellar evolution, setting the stage for the eventual emergence of a planetary nebula and leaving behind a dense white dwarf at the center. Adding another layer of intrigue, Mira exists within a binary system. Its smaller, hotter companion interacts with the red giant, providing a natural laboratory to study mass transfer, gravitational influences, and the broader impact of binary companions on stellar evolution. The red giant's stellar winds feed the companion, offering real-time data on how stars exchange matter and energy, while simultaneously shaping the surrounding interstellar medium. One of the most compelling features of Mira is the predictability of its pulsations. These regular cycles, lasting roughly 11 months, reveal the rhythm of its life and death. Each pulse dredges up material from the star's interior and expels it into space, enriching the galaxy with carbon, oxygen, nitrogen, and other heavy elements forged in the stellar furnace. This recycling process is essential to cosmic chemistry, seeding future stars, planets, and potentially even life itself. Historically, Mira has held a prominent place in astronomical research. Known as the prototype for mirror variables, this star class is defined by dramatic brightness changes occurring over periods from 80 to 1,000 days. The discovery of Mira's variability by David Fabricius in the late 16th century challenged the long-held assumption that stars were immutable points of light, sparking a revolution in observational astronomy. Over the centuries, studies of Mira have revealed the intricate dance of pulsations, mass loss, and binary interactions, shaping modern understanding of the late stages of stellar evolution. Through detailed observation, Mira has illuminated the interplay of forces that govern aging stars. Its pulsations drive powerful stellar winds, shaping the interstellar medium and contributing to galactic chemical evolution. Its binary dynamics offer insight into the exchange of mass and energy between stars, while its gradual shedding of material foreshadows the creation of a planetary nebula. In every sense, Mira embodies both the fragility and resilience of stellar life, a vast, luminous entity slowly disassembling itself, yet leaving behind the essential ingredients for new celestial generations. Ultimately, studying Mira allows astronomers to witness stellar life cycles in action. It connects the fate of distant stars to our own sun, providing a tangible preview of how a seemingly stable main sequence star will transform into a red giant, pulsate, shed its outer layers, and enrich its surroundings with the very elements that make life possible. Mira is not just a star, it is a storyteller, chronicling the processes of creation, transformation, and renewal that define the cosmos itself. Furthermore, the story of material streaming behind Mira as it journeys through the vast expanse of space presents an extraordinary window into the invisible forces shaping our galaxy. Observing this celestial phenomenon allows astronomers to probe the intricate dance between stellar winds and the interstellar medium, a dynamic interaction that profoundly influences the chemical composition and physical structure of the Milky Way. These processes are not just abstract cosmic events. They are the architects of star formation, the sculptors of galactic arms, and the distributors of essential elements that eventually find their way into planets and ultimately life itself. Mira, also known in astronomical circles as Omicron Ceti, has captivated human curiosity for centuries, acting as both a laboratory and a source of wonder. Situated roughly 300 light-years from Earth, This pulsating variable star has consistently defied expectations. Perhaps the most astonishing discovery associated with Mira is its comet-like tail, an immense ribbon of material stretching an extraordinary 13 light-years behind it. First observed in 2007 by NASA's Galaxy Evolution Explorer, this tail is composed of matter that Mira sheds as it moves, revealing how stars actively reshape the environment around them. The existence of such a tail challenged long-standing assumptions about how stars interact with their surroundings and how they enrich the galaxy with the elements forged in their cores. Compounding this intrigue is Mira's companion, known as Mira B. Initially classified as a white dwarf, further study has raised the possibility that it is, in fact, a main sequence star. This subtle reclassification carries far-reaching implications for our understanding of binary star systems, offering new clues about how stars influence one another's evolution over millions, even billions of years. Observations of Mira itself, including its rhythmic pulsations and steady mass loss, provide a vivid preview of the final stages of stellar life, an echo of what awaits our own sun in a distant future. By tracking these behaviors, scientists refine models of stellar evolution, particularly for low and intermediate mass stars approaching the twilight of their existence. Mira's significance extends beyond its scientific revelations. Throughout human history, it has stirred the imagination of civilizations across the globe. Ancient Chinese astronomers meticulously recorded its erratic appearances and disappearances, dubbing it the guest star, a celestial visitor whose presence demanded careful scrutiny. Later, medieval Islamic scholars, most notably the Persian astronomer Abd al-Rahman al-Sufi, referred to it as the wonderful star, making detailed notes on its variable behavior that laid foundational knowledge for future generations. European astronomers would build upon these insights. In the late 17th century, David Fabricius officially documented Mira's fluctuations, while Johannes Hevelius bestowed upon it the Latin name Mira, meaning wonderful or astonishing, a fitting tribute to a star whose brightness waxes and wanes over an 11-month cycle. Across different cultures, Mira's changing light often carried symbolic significance, interpreted as omens, cosmic messages, or the heartbeat of the heavens. In Arabic astronomy, the star's location within the constellation of the celestial sea monster, Cetus, led to names such as Alcetus, the chest of the whale, and descriptors emphasizing its miraculous or remarkable qualities. Native American traditions associated its pulsating light with the rhythm of seasons or imminent events, while its deep red hue at peak brightness linked it to fire, blood, or legendary celestial battles. To the unaided eye, Mira appeared almost alive, vanishing and reappearing in a pattern that defied the long-held belief in the unchanging nature of the night sky. Its variability became a testament to the dynamism of the universe, inviting observers to reconsider the heavens not as static and eternal, but as fluid, evolving, and full of surprises. The meticulous observations of Mira in the late 16th century marked a watershed moment in astronomy. Dutch astronomer David Fabricius was among the first to record its variability, initially mistaking it for a new star, only to witness it fade months later. This discovery shattered the Aristotelian notion of an immutable cosmos and opened the door to a deeper understanding of stellar evolution. Mira became the prototype for an entire class of pulsating red giant stars, now known as Mira variables. Through their study, astronomers gained powerful tools for measuring cosmic distances and tracing the chemical enrichment of galaxies, revealing the intimate connection between individual stars and the broader galactic ecosystem. Beyond its scientific impact, Mira has also inspired generations of artists, writers, and composers. Its unpredictable brightening and fading have served as a metaphor for transformation, the passage of time, and the cyclical nature of existence. From traditional paintings to digital art, literature, and music, creatives have drawn on Mira's pulsating rhythm to explore themes of change, impermanence, and cosmic beauty. The star's dynamic presence, often depicted alongside its companion star, highlights the intricate choreography of binary systems and the interplay of forces in the cosmos. Technological advancements have further amplified our understanding of Mira. High-precision instruments allow astronomers to track its light curve with remarkable accuracy, translating its rhythmic pulsations into vital data about stellar distances, masses, and compositions. The discovery of its enormous tail has prompted fresh questions about how stellar winds interact with the surrounding interstellar medium, illustrating the continuing role of Mira as a catalyst for astronomical innovation. Observations over centuries reveal not a static object, but a living, breathing star system whose behavior enriches both our scientific knowledge and our cultural imagination. From its first documentation in ancient records to its ongoing study with state-of-the-art telescopes, Mira embodies the evolving human relationship with the cosmos. It is a bridge between myth and science, art and mathematics, history and discovery, a luminous reminder that the universe is not a fixed backdrop, but a dynamic, ever-changing tapestry. Every pulse, every fluctuation, and every trailing filament of gas tells a story not just about a single star, but about the forces shaping galaxies, influencing planetary systems, and ultimately touching the narrative of our own existence. Mira, Omicron Ceti, Mira, however it is called, continues to dazzle, inspire, and challenge, proving that the cosmos is as alive and unpredictable as the imagination of those who study it. However, modern observations have painted a far richer and more intricate portrait of this stellar marvel than early astronomers could have imagined. Once thought to be a solitary star, Mira has been revealed through the lens of advanced telescopes and state-of-the-art imaging techniques to be a binary star system, a cosmic duet composed of a massive red giant, Mira A, and its smaller, less luminous companion, Mira B. The interplay between these two stars is nothing short of mesmerizing. Streams of material flow from the swollen red giant to the smaller star, creating a dynamic stellar choreography that has fascinated scientists and skywatchers alike. Observatories positioned beyond Earth's atmosphere, including the Hubble Space Telescope, have offered unprecedented clarity, capturing features invisible to generations of astronomers who relied solely on ground-based instruments. Among the most astonishing discoveries is a vast, comet-like tail of stellar debris, stretching an astonishing 13 light-years behind Mira, a testament to the star's ceaseless shedding of material as it moves through the interstellar medium. The spectroscopic revolution has allowed astronomers to peer deep into Mira's very essence, revealing not just its chemical composition, but also the subtleties of its rhythmic behavior. Mira A is now recognized as a pulsating variable star, expanding and contracting over a period of roughly 11 months. Its pulsations, combined with the gravitational influence of Mira B, produce a complex and ever-changing stellar environment, one that continues to challenge theoretical models and deepen our understanding of stellar physics. This remarkable celestial object, also catalogued as Omicron Ceti, has captivated human observers for centuries. Situated in the constellation Cetus, Mira was first documented by David Fabricius in 1596, who noticed that the star periodically brightened and dimmed, a phenomenon unlike anything known at the time. Fabricius' discovery established Mira as the first variable star ever recorded, opening an entirely new field of astronomical inquiry. Decades later, in 1638, Johannes Holwarda calculated the star's variability period to be roughly 11 months, solidifying its role as a critical object of study. Its evocative name, meaning wonderful or astonishing in Latin, was bestowed by Johannes Hevelius in 1662, reflecting the awe it inspired in early modern astronomers. By the 19th century, investigations had entered a more scientific phase. Father Angelo Secchi, a pioneer in astronomical spectroscopy, examined Mira's spectrum in 1866, demonstrating that its brightness fluctuations coincided with shifts in its spectral signature. This insight provided the first tangible evidence linking the star's observable behavior to underlying physical processes, laying the groundwork for modern stellar astrophysics. More recently, in 2007, the Galaxy Evolution Explorer spacecraft unveiled the star's 13 light-year-long tail of ejected material, highlighting how stars interact with and enrich the interstellar medium over cosmic timescales. Mira's significance extends far beyond professional astronomy. Its dramatic cycles of brightening and dimming provide a unique window into the life of a star, showing the public that the night sky is alive with dynamic and evolving phenomena. The discovery of Mira-type variables named after this archetypal star has allowed scientists to map distances across the cosmos and investigate the late stages of stellar evolution. Amateur astronomers can actively participate in tracking Mira's cycles, contributing valuable observations and fostering a sense of shared discovery, making the star an enduring bridge between professional research and public curiosity. Across cultures and eras, Mira has held diverse symbolic significance. In Latin, its name captures the awe it inspires. In ancient Arabic, it was called Alomar, the whale, linking it to the mythological creature represented by Cetus. In Hindu astrology, Mira is associated with the nakshatra Chitra, a lunar mansion representing brilliance and creativity, reflecting the star's fluctuating luminosity. Chinese astronomers integrated it into their neck mansion within the black tortoise of the North constellation, symbolizing imperial significance. These cultural connections illustrate how celestial objects transcend human language and geography, becoming shared points of wonder and inspiration across civilizations. From a scientific perspective, Mira's binary nature and pulsating behavior make it a fascinating laboratory for exploring planetary dynamics. Its red giant phase, marked by intense stellar winds and radiation, would pose profound challenges for any nearby planets, potentially stripping atmospheres or altering orbital stability. The gravitational pull of the smaller white dwarf companion adds another layer of complexity, influencing planetary orbits and introducing instability over astronomical timescales. Yet, the same processes could provide raw material for future planet formation, illustrating the dual role of stars as both destroyers and creators within the cosmic cycle. Mira, the astonishing variable star of Cetus, thus embodies both the grandeur and complexity of the universe. Its history, from early observations in the 16th century to contemporary space-based studies, reflects humanity's evolving capacity to probe the cosmos. Its pulsations, tail, and binary interactions continue to challenge astronomers, while its visibility and cultural significance inspire curiosity and wonder, inviting all who look skyward to witness the dynamic story of a star that is far from ordinary. However, this intricate cosmic choreography may also carve out pockets of relative calm, regions where planets could achieve stable orbits, tracing wide, sweeping paths around both stars. Recent telescopic observations have revealed the presence of a protostellar disk enveloping Mira, a swirling expanse of gas and dust that hints at the birth of planetary bodies. Though no planets have yet been definitively confirmed within this system, the mere existence of this disk is a tantalizing clue. The raw ingredients for planets are present, and the processes of planetary assembly are likely underway. In many ways, the Mira system stands as a natural laboratory, a celestial stage on which scientists can observe how planets might form, migrate, and adapt in the challenging gravitational fields surrounding aging stars. Mira, also cataloged as Omicron Ceti, is a star of extraordinary character, one whose brightness ebbs and surges dramatically over time. These pulsations are not minor. They profoundly affect any hypothetical planets orbiting the star. As Mira swells and contracts, both its size and luminosity fluctuate enormously, subjecting any orbiting worlds to extreme swings in light and heat. At its most radiant, Mira can shine 1,000 times more brilliantly than during its dimmest phases. Imagine a planet bathed in relentless intensity one moment, only to drift into long stretches of near darkness the next. These dramatic thermal oscillations would present formidable obstacles for the emergence or survival of life as we understand it. The star's changing girth also alters the gravitational forces experienced by orbiting planets. Each expansion and contraction modifies the tidal stresses on these worlds, potentially triggering heightened volcanic activity, tectonic shifts, and surface instability. Adding to these challenges, Mira steadily loses mass through its powerful stellar winds. This gradual shedding of material changes the star's gravitational grip over time, subtly altering planetary orbits and perhaps even nudging some planets into new trajectories. Meanwhile, the stellar wind itself, charged with particles racing outward at thousands of kilometers per hour, could strip away planetary atmospheres, further reducing the chances for stable, life-supporting conditions. Situated in the constellation Satis, Mira exemplifies the difficulties astronomers face when trying to detect planets around variable stars. Its pulsations, recurring over a cycle of approximately 332 days, create a moving target for exoplanet hunters. Many detection methods, such as the transit technique, rely on precise measurements of a star's brightness. Tiny dips in luminosity often reveal the presence of orbiting planets. But in the case of Mira, its own intrinsic fluctuations can obscure or imitate these planetary signals, making it exceptionally difficult to differentiate between stellar variability and a genuine planetary transit. Similarly, the radial velocity method, which tracks the minute wobble of a star caused by an orbiting planet's gravitational tug, is complicated by Mira's turbulent pulsations and unstable outer layers. The star's own motion can drown out the delicate signals that betray the presence of planets. The red giant status of Mira further complicates the picture. Stars like Mira expand dramatically in their later stages, sometimes consuming or destabilizing the orbits of inner planets and reshaping the architecture of their planetary systems. Consequently, predicting where planets may reside or how they interact with an evolving star becomes a delicate and an uncertain task, requiring sophisticated models and careful observation. Yet, studying Mira yields profound scientific rewards. The star functions as a cosmic laboratory where researchers can investigate the interplay between an aging star and its surrounding environment. As Mira pulsates, it expels vast quantities of gas and dust into space, creating a dynamic atmosphere that mirrors conditions potentially encountered by exoplanets orbiting similar stars. By analyzing the composition and behavior of this material, astronomers gain insights into how planetary atmospheres might develop and evolve under the influence of stellar aging. The star's variability has direct implications for habitability. As Mira cycles through periods of expansion and contraction, the location of its habitable zone, the region where liquid water could exist on a planet's surface, shifts continuously. Any orbiting worlds would experience radical swings in temperature, their atmospheres alternately freezing and thawing. This cycle could accelerate atmospheric loss, dramatically challenging the prospects for life. Moreover, intense stellar winds during bright phases could strip away remaining atmospheres, creating barren, inhospitable worlds. Nevertheless, these extreme conditions also inspire speculation about resilience and adaptability. Some scientists propose that life, if present, might evolve strategies akin to hibernation or migration, much like organisms on Earth respond to seasonal changes, illustrating the potential versatility of life in diverse cosmic environments. Mira's long-term evolution is no less dramatic. Over hundreds of millions of years, the star will continue expanding, eventually entering a full red giant phase, where it may engulf inner planets entirely. Outer planets, if any survive, will be exposed to relentless stellar radiation and wind, potentially losing their atmospheres and undergoing profound environmental transformations. Ultimately, Mira will shed its outer layers, forming a glowing planetary nebula with a dense white dwarf at its heart. Any surviving planets would then orbit this remnant, bathed in its cooling glow and surrounded by the remnants of the star's former grandeur, a planetary environment unlike anything observed in our own solar system. Despite the formidable challenges posed by variable stars like Mira, astronomers have pressed onward. In 2007, a possible planet was reported orbiting the Mira-type star R Sculpturus, a gas giant several times more massive than Jupiter, situated approximately 1.5 times the Earth-Sun distance from its host. While confirmation remains debated, such findings hint at the tantalizing possibility that planets can form and endure even in these turbulent systems. Advances in observational techniques promise further discoveries, potentially revealing new insights into planetary formation and evolution around evolved pulsating stars. Mira itself is part of a binary system, paired with a smaller companion, likely a white dwarf. Their mutual orbit produces a gravitational ballet that profoundly influences the potential for planet formation. The constant tug and pull create regions of instability where planetary building blocks are jostled and scattered, complicating the assembly of planets from dust and gas. Despite this turbulence, the system remains an extraordinary natural experiment. demonstrating the delicate balance required for planets to form and endure in environments governed by strong and fluctuating gravitational forces. In essence, Mira exemplifies the extraordinary complexity of stellar evolution and planetary dynamics. From its pulsating luminosity to its violent stellar winds, from its shifting habitable zone to its binary interactions, the system challenges every assumption about how and where planets might exist. Yet it is precisely this complexity that makes Mira so invaluable to astronomers. It offers a living, evolving example of the forces that shape worlds, a window into the fate of planets orbiting aging stars, and a reminder of the astonishing diversity and resilience of the cosmos. Furthermore, the pulsating behavior of Mira A introduces an extraordinary level of complexity to this already dynamic star system. As this red giant expands and contracts with a rhythmic, almost breathing motion, it ejects colossal amounts of material into the surrounding space. Streams of gas and stellar debris are cast outward, sweeping away any nascent planets or protoplanetary disks that might have been slowly coalescing. The fierce stellar winds that accompany these pulsations do not merely disperse matter, they heat and agitate nearby gas and dust, creating a chaotic and turbulent environment that makes the formation of stable planetary bodies exceedingly difficult. Adding to this celestial ballet, Mira B, a compact white dwarf companion, exerts its own gravitational pull on the environment. Material expelled from Mira A can be drawn toward Mira B, forming a dense accretion disk around the smaller star. This phenomenon not only competes with potential planet formation, but also generates a dynamic system where long-term planetary stability is nearly impossible. The interplay between these two stars transforms the Mira system into a place of both scientific fascination and hostile conditions, where the birth of planets is constantly challenged by the raw forces of stellar evolution. From the perspective of a planet daring enough to orbit within this binary system, the sky would be an ever-changing spectacle of light and shadow. Mira A, the dominant red giant, would loom enormous in the heavens, a deep crimson sphere dwarfing the familiar sun seen from Earth. Its pulsations would produce dramatic swings in illumination, bathing the landscape in a fiery glow during peaks of brightness, then plunging it into relative darkness when the star contracts. Mira B, in stark contrast, would appear as a bright bluish-white point of light, orbiting around its giant companion once every 5 centuries, and adding a subtle shifting contrast to the celestial panorama. The combination of intense radiation and powerful stellar winds from both stars would interact with the planet's atmosphere, potentially generating shimmering auroras that stretch across the sky. Gases ionized by the stellar output would glow in vibrant colors, undulating in response to the winds and magnetic forces, producing a constantly shifting, almost hypnotic light show. This dramatic skyscape is a testament to the sheer power and complexity of binary systems like Mira, offering observers a cosmic theater of both beauty and danger. Mira, also known as Omicron City, provides critical insights into the life cycle of stars and the distribution of elements necessary for planetary formation. The pulsations of Mira A shed its outer layers into space, enriching the interstellar medium with heavy elements that form the building blocks for future stars, planets, and potentially life. This shedding process allows astronomers to study how dying stars recycle material across the galaxy, seeding new systems with the ingredients required for life to emerge. The gravitational dance between Mira A and its white dwarf companion also sheds light on the stability of binary systems, helping scientists understand how planets might survive, or fail to survive, around such stars. The extreme conditions present in Mira offer a natural laboratory for studying high-energy astrophysical processes, enabling researchers to refine their models for planetary formation and the detection of biosignatures in distant star systems. The challenges for life in such an environment are profound. The red giant's variability produces extreme fluctuations in temperature and radiation, constantly shifting the boundaries of the habitable zone. Any planet in orbit around Mira would experience violent swings in climate, potentially making the development of complex life exceptionally difficult. Yet, the possibility of life should not be entirely dismissed. If organisms were to arise in this system, they would need to evolve extraordinary adaptations, perhaps developing biological or technological mechanisms to cope with periodic bursts of radiation and drastic temperature shifts. Advanced civilizations might even harness the pulsations of Mirror A as a power source or develop protective infrastructure to withstand its periodic intensification. The presence of Mirror B adds another layer of opportunity amid the danger. As a stable white dwarf, it could provide supplemental energy, potentially moderating some of the environmental extremes caused by its red giant companion. The combination of these two stars creates a binary system of contrasts. One star massive, radiant, and unstable, the other compact, bright, and comparatively steady. The juxtaposition of these forces makes Mirror not only an inhospitable environment for most forms of life, but also a fascinating subject for exploring the resilience and adaptability of life in extreme conditions. The luminosity of Mirror A varies by roughly a factor of 1,000 over an 11-month cycle, a scale of fluctuation almost impossible to imagine. For any hypothetical planet orbiting within the system, the consequences would be dramatic. Periods of intense radiation and heat could disrupt atmospheres, melt surface ice, or even drive chemical reactions at accelerated rates, while the dim phases might plunge the planet into cold, near-total darkness. Life here would have to withstand extremes far beyond anything experienced on Earth, developing mechanisms for surviving both intense energy surges and periods of deprivation. In sum, the Mira system, Omicron City, stands as a testament to the violent beauty of the universe. Its pulsating red giant, dynamic white dwarf companion, and the interplay of massive stellar winds and ejected material create a theater of cosmic forces in perpetual motion. For scientists, it offers an unparalleled opportunity to study stellar evolution, binary interactions, and the challenges of planetary formation in extreme environments. For hypothetical observers or life forms, it would be a world of awe-inspiring light, extreme change, and the ever-present reminder that the universe is a place of both wonder and unrelenting power. However, it is crucial to appreciate the astonishing adaptability of life itself. Across the vast expanse of the cosmos, life has proven that it can flourish in environments far more extreme than anything we might consider hospitable. On Earth alone, extremophiles, organisms that thrive under conditions once deemed impossible, inhabit scalding hydrothermal vents, the crushing depths of the oceans, and the frozen wastes of polar regions. These examples reveal that the presence of a variable star with all its dramatic swings and instability does not necessarily rule out the possibility of life taking hold. On the contrary, the unique and turbulent conditions around a star like Mirror could act as a crucible, fostering the emergence of highly specialized, resilient organisms capable of surviving extremes of radiation, temperature, and atmospheric composition, life forms unlike anything known in our solar system. Mirror, also designated Omicron Ceti, has long captured the fascination of astronomers and the search for extraterrestrial intelligence, Ceti community. Situated approximately 300 light-years from Earth, this long-period variable star exhibits behaviors and characteristics that make it an exceptional candidate for detailed study. The SETI Institute has included Mirror in its ongoing programs for radio observation, employing the Allen Telescope Array, a sophisticated network of radio dishes purpose-built for detecting potential artificial signals. Researchers focus on stars like Mirror not only because of their unique properties, but also due to their age and stability. As an asymptotic giant branch star, Mira represents a late stage of stellar evolution, meaning any planetary civilizations in its orbit would have had billions of years to emerge and develop. The presence of a companion white dwarf adds further complexity, creating a dynamic and ever-shifting environment where life would need to be extraordinarily adaptable. The challenges for any civilization orbiting Mira would be extraordinary. The star itself is a pulsating red giant, expanding and contracting over time, with luminosity fluctuating by a factor of roughly 1,000 over a cycle of approximately 11 months. Such radical variation in light and heat presents an immediate threat. During peak brightness, planets could be scorched under intense radiation, while dimmer periods might plunge them into prolonged darkness and bitter cold. This unrelenting cycle would demand that life, or the civilization, develop strategies to endure extreme environmental swings, perhaps evolving biological or technological adaptations far beyond what humanity currently understands. Mira's instability extends beyond its luminosity. The star is actively shedding its outer layers, generating a stellar wind that stretches over 13 light-years behind it, forming a cosmic tail of gas and dust. This ongoing mass loss could gradually strip away planetary atmospheres, exposing worlds to harsh space conditions. As Mira edges toward the final phases of its life, it will eventually expel its outer layers entirely, leaving behind a dense white dwarf. Any civilization attempting long-term survival in this system would require advanced engineering, either to harness the star's energy or to migrate beyond the system entirely, a monumental task by any measure. Despite these dangers, the energy potential of a Mira-type star is staggering. During its luminous phases, the star radiates as much as 10,000 times the energy output of our Sun. For an advanced civilization capable of stellar-scale engineering, this represents a near-limitless source of power. Concepts like a partial Dyson sphere or an intricate Dyson swarm could allow the civilization to capture this energy. Such structures, composed of millions of collectors orbiting the star, would need to withstand immense radiation and gravitational stress, while dynamically adjusting to the pulsations and variable output of the star. Beyond direct energy capture, the immense stellar winds and ejected material could serve as resources, offering raw matter for construction, fuel, or even propulsion for interstellar colonization. Mira leaves a spectacular cosmic footprint. Its trail of expelled stellar material stretching 13 light-years across the galaxy could in principle serve as a medium for interstellar communication. Advanced civilizations might manipulate the trail's density, chemical composition, or structure to encode messages, creating a signal visible across enormous distances. The longevity of this trail, persisting for thousands of years, offers a remarkable potential for transmitting information far beyond the immediate vicinity of the star. Yet the practical challenges of such an endeavor are immense. The energy requirements, the timescales involved, and the technical expertise needed all remain well beyond current human capabilities. For now, the idea exists primarily in the realm of speculation and visionary science fiction. Studying stars like Mira provides invaluable insight into the broader quest to understand habitable worlds. The pulsating nature of these stars allows astronomers to measure their mass, composition, and size with exceptional precision, shedding light on the late stages of stellar evolution. By understanding how red giants age, expand, and lose mass, scientists can infer the likelihood that planets could form, survive, and support life in such systems. These insights inform predictions about the stability of stars, the duration of habitable zones, and the potential for complex life to develop in distant star systems. Mira-type stars, ancient and cool as they approach the ends of their lives, offer a window into the far future of stars like our own Sun, and provide a roadmap for identifying other regions in the galaxy where life might find a foothold, even in the face of extraordinary challenges. Furthermore, Mira stars are extraordinary engines of cosmic transformation, continuously expelling enormous quantities of gas and dust into the vast expanse of space. This ejected material, rich with heavy elements forged in the hearts of these stars, plays a pivotal role in shaping the chemical tapestry of the galaxy. Elements like carbon, oxygen, and iron, essential building blocks for rocky planets and ultimately the molecules that underpin life, are scattered far and wide, seeding regions of interstellar space where new stars and planetary systems may one day arise. By meticulously analyzing the composition of the matter hurled from Mira-type stars, astronomers can reconstruct the chemical evolution of galaxies, unraveling how different cosmic environments influence the potential for planet formation and perhaps the emergence of life itself. The rhythmic pulsations of Mira stars provide an additional window into the complex interplay of stellar atmospheres. These pulsations, periodic expansions and contractions of the star's outer layers, reveal the dynamic conditions that would affect any orbiting planets. Understanding these processes is not merely an academic exercise. It directly informs the search for habitable worlds. Variations in stellar activity, radiation output, and atmospheric behavior can dramatically reshape a planet's climate and surface conditions, potentially rendering a once hospitable world barren. By studying these stellar patterns, scientists can refine their criteria for habitability, prioritizing star systems where life has the best chance of surviving and thriving. When examining Mira-like systems for potential biosignatures, researchers focus on a range of indicators that could hint at biological activity. Mira-type stars, often cool red giants, present both unique obstacles and intriguing opportunities in this quest. One promising biosignature is methane in a planet's atmosphere. On Earth, methane is primarily produced by living organisms, and its presence in combination with oxygen in another planetary environment could suggest ongoing biological processes. Water vapor is another crucial indicator. While water alone is not definitive proof of life, its existence is essential for life as we understand it. In the extended habitable zones around Mira stars, planets with the right conditions could harbor liquid water, making them compelling targets for further study. Moreover, scientists seek signs of photosynthesis or analogous light harvesting mechanisms. In systems dominated by infrared light, typical photosynthetic pigments would be ineffective, suggesting that life might adapt in novel ways. Researchers would search for unique spheric absorption patterns or surface reflectance signatures that reveal such adaptations, expanding our understanding of how life could evolve under very different stellar conditions. The binary star system, known as Mira, or Omicron City, exemplifies the complexity and beauty of these cosmic environments. Situated approximately 350 light-years from Earth, this system consists of Mira A, a red giant, and Mira B, a smaller companion, likely a white dwarf. The gravitational dance between these two stars creates an intricate and often unstable environment for any planets caught in their orbit. Such gravitational turbulence could lead to extreme temperature swings and unpredictable orbital paths, making sustained habitability extraordinarily difficult. Mira A itself is a pulsating variable star, with its brightness waxing and waning over a cycle of roughly 330 days. These pulsations drive a stellar wind that carries material far into space, a force compounded by radiation from both stars in the binary system. Any planets in the vicinity would face relentless atmospheric stripping, intense radiation, and volatile conditions, presenting formidable challenges for life as we know it. Furthermore, Mira A's evolutionary stage as a red giant indicates that any planets that might have once supported life would now be exposed to conditions likely too extreme for survival. Observing Mira provides astronomers with a rare glimpse into the long-term evolution of stars and their influence on surrounding planetary systems. As Mira sheds mass and expands, it creates a tail of debris extending an astonishing 13 light-years behind it. This ongoing mass loss reshapes the stellar environment, affecting nearby celestial bodies and providing critical insights into the life cycle of stars similar to our Sun. By understanding how aging stars like Mira alter their neighborhoods, scientists gain perspective on how habitable zones shift over time, potentially rendering previously life-friendly planets uninhabitable. Additionally, Mira demonstrates how aging stars act as cosmic alchemists, distributing heavy elements throughout their surroundings. These elements, vital for forming new planets and supporting potential life, contribute to the continuous recycling and enrichment of the interstellar medium. By studying such systems, astronomers deepen their understanding of stellar life cycles, the genesis of planetary systems, and the complex conditions that may foster or hinder life across the universe. In turn, this knowledge illuminates the past, present, and potential future of our own solar system, connecting the fate of distant stars to the story of life on Earth.